fastest supercomputer.
To make sure that our quantum advantage demonstration was more than just a one-off experiment, we're also hard at work making it available to all the users of Xanadu Cloud.
Everyone came together, from quantum theorists to engineers to developers, for the final push to make quantum advantage available on the Xanadu Cloud.
The last weeks were spent chasing bugs, connectivity, and stability issues, making sure that this device had the operational readiness that is expected of cloud-available quantum hardware. The last mile was the integration of the hardware with one of our open source quantum programming frameworks, Strawberry Fields. Now, for the first time ever, anyone, no matter where they are, can run their own quantum advantage experiments.
Xanadu's demonstration of quantum advantage is not the final word, but it is an enormous step towards the ultimate goal of a fault-tolerant quantum computer. And it is more evidence of the power of teamwork, the power of light, and the power of quantum.
A quantum computer with 1 million qubits is this decade's technological holy grail. With the help of photonics, Xanadu is building a universal and fault-tolerant quantum computer capable of scaling to 1 million qubits. A single module of the computer consists of 4 components. The state preparation component is where many qubits are generated with some probability. Then, a multiplexer increases this probability to make sure that a qubit always emerges. In the stitcher, the qubits are entangled into a special quantum state required for universal and fault-tolerant computation. Finally, the quantum processing unit, or QPU, measures the state, using the outcomes both to correct for errors and perform the computation. Let's look at each component in more detail. First up is state preparation. While Xanadu's current photonic chips work like little quantum computers themselves, they are also components of a more powerful machine. They can be used to prepare robust photonic qubits, special states of many photons with built-in error correction ability. A qubit can be created by counting the photons in all but one of the outputs of a state preparation chip. Photons are counted by transition edge sensors, the only part of the computer operating at low temperatures. Seeing a specific photon number pattern indicates that a qubit has been successfully generated and is ready for use at the remaining port. Next is the multiplexer. To boost the likelihood that a qubit emerges, many state preparation chips must be multiplexed. This means they are connected to a large network of optical switches which route successfully prepared states to the next step of the computation. Still, multiplexing cannot boost the probability of getting a qubit to 100%. That would require far too many chips, detectors, and switches. Instead, the system can make up for the occasional no-show by swapping in an ordinary squeeze state. While squeeze states are not able to correct errors by themselves, they still behave like qubits and can be generated without fail whenever you need them. Let's move on to the stitcher. Any useful quantum computer needs to create entanglement. Instead of entangling qubits as we go, there is a lot to gain by generating all the entanglement at the beginning. In the stitching component, beam splitters knit together the qubits in space and time to produce a 3-dimensional highly entangled state called a cluster state. Only a few layers of this state exist at any given time, simplifying its construction. The 3 dimensions help give the quantum computer its fault tolerance. While a small error can be caught and corrected by a single qubit, a larger error can be flagged by looking at a group of many qubits. A box of physical qubits comprises a single logical qubit. Finally, we arrive at the QPU, or quantum processing unit. In the cluster state model, seeing is computing. A measurement of the state isn't simply a readout of the computation, it is the computation. Measuring the electromagnetic field of the pulse of light that makes up each node in the cluster, done with room temperature photodetectors, has the same effect as applying a quantum gate. A quantum algorithm then becomes a recipe of which measurements to perform in the QPU. This model of quantum computing is completely equivalent to the traditional gate model. No single module can hold 1 million qubits. To scale efficiently, the qubits must be distributed among many modules networked together. Here, photonics has a distinct advantage: the ability to send qubits between modules using optical fibers, the same type that brings the internet to your home or office. Also vital is the ability to mass produce all the required chips. Each component in Xanadu's quantum computer can be manufactured at scale using standard processes and foundries, the same ones that make the chips inside your phone or laptop. These techniques have been refined over many decades in the electronics and telecommunications industry. The ability to leverage mass manufacturing and networkability leads to an exciting conclusion. Photonics is leading the way to a fault-tolerant quantum computer with 1 million qubits this decade. Learn more at xanadu.ai. A quantum computer with 1 million qubits is this decade's technological holy grail, scaling to 1 million tolerant computation. Finally, the quantum processing unit, or QPU. A quantum computer with 1 million qubits is this decade's technological holy grail. With the help of photonics, Xanadu is building a universal and fault-tolerant quantum computer capable of scaling to 1 million qubits. A single module of the computer consists of 4 components. The state preparation component is where many qubits are generated with some probability. Then, a multiplexer increases this probability to make sure that a qubit always emerges. In the stitcher, the qubits are entangled into a special quantum state required for universal and fault-tolerant computation. Finally, the quantum processing unit, or QPU, measures the state, using the outcomes both to correct for errors and perform the computation. Let's look at each component in more detail. A quantum computer with 1 million qubits is this decade's technological holy grail. With the help of photonics, Xanadu is building a universal and fault-tolerant quantum computer capable of scaling to 1 million qubits. A single module of the computer consists of 4 components. The state preparation component is where many qubits are generated with some probability. Then, a multiplexer increases this probability to make sure that a qubit always emerges. In the stitcher, the qubits are entangled into a special quantum state required for universal and fault-tolerant computation. Finally, the quantum processing unit, or QPU, measures the state, using the outcomes both to correct for errors and perform the computation. Let's look at each component in more detail. First up is state preparation. While Xanadu's current photonic chips work like little quantum computers themselves, they are also components of a more powerful machine. They can be used to prepare robust photonic qubits, special states of many photons with built-in error correction ability. A qubit can be created by counting the photons in all but one of the outputs of a state preparation chip. Photons are counted by transition edge sensors, the computer operating at low temperatures. Seeing a specific photon number pattern indicates that a qubit has been successfully generated and is ready for use at the remaining port. Next is the multiplexer. To boost the likelihood that a qubit emerges, many state preparation chips must be multiplexed. They are connected to a large network of optical switches which route successfully prepared states to the next step of the computation. Still, multiplexing cannot boost the probability of getting a qubit to 100%. That would require far too many chips, detectors, and switches. Instead, the system can make up for the occasional no-show by swapping in an ordinary squeeze state. While squeeze states are not able to correct errors by themselves, they still behave like qubits and can be generated without fail whenever you need them. Let's move on to the stitcher. Any useful quantum computer needs to create entanglement. Instead of entangling qubits as we go, there is a lot to gain by generating all the entanglement at the beginning. In the stitching component, beam splitters knit together the qubits in space and time to produce a three-dimensional highly entangled state called a cluster state. Only a few layers of this state exist at any given time, simplifying its construction. The three dimensions help give the quantum computer its fault tolerance. While a small error can be caught and corrected by a single qubit, a larger error can be flagged by looking at a group of many qubits. A box of physical qubits comprises a single logical qubit. Finally, we arrive at the QPU, or Quantum Processing Unit. In the cluster state model, seeing is computing. A measurement of the state isn't simply a readout of the computation, it is the computation. Measuring the electromagnetic field of the pulse of light that makes up each node in the cluster, done with room temperature photodetectors, has the same effect as applying a quantum gate. A quantum algorithm then becomes a recipe of which measurements to perform in the QPU. This model of quantum computing is completely equivalent to the traditional gate model. No single module can hold 1 million qubits. To scale efficiently, the qubits must be distributed among many modules networked together. Here, photonics has a distinct advantage: the ability to send qubits between modules using optical fibers, the same type that brings the internet to your home or office. Also vital is the ability to mass produce all the required chips. Each component in Xanadu's quantum computer can be manufactured at scale using standard processes and foundries, the same ones that make the chips inside your phone or laptop. These techniques have been refined over many decades in the electronics and telecommunications industry. The ability to leverage mass manufacturing and networkability leads to an exciting conclusion. Photonics is leading the way to a fault-tolerant quantum computer with 1 million qubits this decade. Learn more at xanadu.ai.
Imagine controlling a computer the temperature of interstellar space, connecting to the basic elements of the universe from your laptop, crunching numbers using the vibrations of particles, running computer programs directly on a cloud of atoms, solving hard problems with frickin' laser beams. Welcome to the awesome realm of quantum computing. Welcome to PennyLane. PennyLane is open source software for programming quantum computers. You may have heard the hype about the power of quantum computers. Some of it is even true. Right now, trailblazers worldwide are building a new technology unlike anything we've seen before. But the world of quantum computing is still wild, still untamed. Quantum computers should be useful and available to people everywhere. We're on our way, but there's much more to build, much more to discover. They say it takes a village. All of us, a global community, working together to bring quantum computing into its full potential. It's gonna be amazing. Imagine studying the most inscrutable properties of molecules by using other molecules, training a quantum computer the same way as a neural network, connecting to every quantum computer available today, or even combining them together to make something greater than the sum of its parts to unlock the full power of quantum computers. We'll need to do things no one has ever done before, things no one has even thought of doing before. It's going to take big ideas, new ideas, your ideas, teachers, students, scientists, artists, enthusiasts. Thousands of people worldwide have already joined PennyLane's quantum computing community. Everyone has a part to play, a unique contribution to make. What will yours be? Imagine learning the latest in quantum computing from the biggest experts in the field, studying on the shoulders of giants, and seeing further than anyone before, leaving your own mark on this historic technology. If we can imagine it, we can build it, create it, share it, together. Imagine controlling a computer the temperature of interstellar space, connecting to the basic elements of the universe from your laptop, crunching numbers using the vibrations of particles, running computer programs directly on a cloud of atoms, solving hard problems with frickin' laser beams. Welcome to the awesome realm of quantum computing. Welcome to Penny Lane. Penny Lane is open source software for programming quantum computers. You may have heard the hype about the power of quantum computers. Some of it is even true. Right now, trailblazers worldwide are building a new technology unlike anything we've seen before. But the world of quantum computing is still wild, still untamed. Quantum computers should be useful and available to people everywhere. We're on our way, but there's much more to build, much more to discover. They say it takes a village. All of us, a global community, working together to bring quantum computing into its full potential. It's gonna be amazing. Imagine studying the most inscrutable properties of molecules by using other molecules, training a quantum computer the same way as a neural network, connecting to every quantum computer available today, or even combining them together to make something greater than the sum of its parts to unlock the full power of quantum computers. We'll need to do things no one has ever done before, things no one has even thought of doing before. It's going to take big ideas, new ideas, your ideas. Teachers, students, scientists, artists, enthusiasts. Thousands of people worldwide have already joined Penny Lane's quantum computing community. Everyone has a part to play, a unique contribution to make. What will yours be? Imagine learning the latest in quantum computing from the biggest experts in the field, studying on the shoulders of giants, and seeing further than anyone before, leaving your own mark on this historic technology. If we can imagine it, we can build it, create it, share it, together.
A quantum computer with 1 million qubits is this decade's technological holy grail. With the help of photonics, Xanadu is building a universal and fault-tolerant quantum computer capable of scaling to 1 million qubits. A single module of the computer consists of 4 components. The state preparation component is where many qubits are generated with some probability. Then, a multiplexer increases this probability to make sure that a qubit always emerges. In the stitcher, the qubits are entangled into a special quantum state required for universal and fault-tolerant computation. Finally, the quantum processing unit, or QPU, measures the state, using the outcomes both to correct for errors and perform the computation. Let's look at each component in more detail. First up is state preparation. While Xanadu's current photonic chips work like little quantum computers themselves, they are also components of a more powerful machine. They can be used to prepare robust photonic qubits, special states of many photons with built-in error correction ability. A qubit can be created by counting the photons in all but one of the outputs of a state preparation chip. Photons are counted by transition edge sensors, the only part of the computer operating at low temperatures. Seeing a specific photon number pattern indicates that a qubit has been successfully generated and is ready for use at the remaining port. Next is the multiplexer. To boost the likelihood that a qubit emerges, many state preparation chips must be multiplexed. This means they are connected to a large network of optical switches which route successfully prepared states to the next step of the computation. Still, multiplexing cannot boost the probability of getting a qubit to 100%. That would require far too many chips, detectors, and switches. Instead, the system can make up for the occasional no-show by swapping in an ordinary squeeze state. While squeeze states are not able to correct errors by themselves, they still behave like qubits and can be generated without fail whenever you need them. Let's move on to the stitcher. Any useful quantum computer needs to create entanglement. Instead of entangling qubits as we go, there is a lot to gain by generating all the entanglement at the beginning. In the stitching component, beam splitters knit together the qubits in space and time to produce a three-dimensional, highly entangled state called a cluster state. Only a few layers of this state exist at any given time, simplifying its construction. The three dimensions help give the quantum computer its fault tolerance. While a small error can be caught and corrected by a single qubit, a larger error can be flagged by looking at a group of many qubits. A box of physical qubits comprises a single logical qubit. Finally, we arrive at the QPU, or quantum processing unit. In the cluster state model, seeing is computing. A measurement of the state isn't simply a readout of the computation, it is the computation.
Interesting, right?
Measuring the electromagnetic field of the pulse of light that makes up each node in the cluster, done with room temperature photodetectors, has the same effect as applying a quantum gate. A quantum algorithm then becomes a recipe of which measurements to perform in the QPU. This model of quantum computing is completely equivalent to the traditional gate model. No single module can hold 1 million qubits. To scale efficiently, the qubits must be distributed among many modules networked together. Here, photonics has a distinct advantage: the ability to send qubits between modules using optical fibers, the same type that brings the internet to your home or office. Also vital is the ability to mass produce all the required chips. Each component in Xanadu's quantum computer can be manufactured at scale using standard processes and foundries, the same ones that make the chips inside your phone or laptop. These techniques have been refined over many decades in the electronics and telecommunications industry. The ability to leverage mass manufacturing and networkability leads to an exciting conclusion. Photonics is leading the way to a fault-tolerant quantum computer with 1 million qubits this decade. Learn more at xanadu.ai.
We're going to go to Strawberry Field site. We'll find it. Where's the Chrome? Interesting.
This is Dave, head of marketing at a ketchup company, about to use Grammarly to
suggest a fix for a library that's got like that it thinks like that has seen on GitHub a lot, and now in your company you're not using that library, so now it will give you a fix that it thinks is right, but it's not good for you. So you have to be kind of very careful with this stuff. Okay, so this is a good question. So I don't think like I'm very careful never to mention the word AI. It's machine learning, right? It's like it has nothing to do with intelligence. It knows whatever you train it on, but it's not kind of creative. What is it, Michael? Like unlike Michael, right? Michael is like actually got like like are you artificially intelligent? Are you a robot or are you kind of like a human?
I'm trying to influence you to stop your presentation because you should start your presentation.
All right, sounds good.
That's. I'm sorry, Henrik. Your question is down the drain. Oh, right. Hello, everybody. My name is Michael. I'm running Foo Café together with Ellie here in Stockholm, and super great to see you here, and Eric. Eric should have been here in the spring. That
oh my goodness.
Yeah. And we planned it. I think it was a year ago, we planned it. Yeah, I will be in Sweden in the spring, so I could do a talk at Focafé Stockholm. Awesome. And then we came into April, May, and then Eric sent all the information as you should. Yeah, everything worked out fine. And I posted the event on our website, and I asked Eric to check it out. And he said, it looks good, but it's the wrong city. I can't be in Stockholm because my plans is, I thought it was Malmö, and yeah. And then he saw that he made a mistake, and he said, all right, in that case, I will come back to Stockholm in the fall. And the funny thing, the rest of the story is quite funny, because just a few months ago, or 1 month ago, something like that, Cecilia from Factor 10 asked me, could we do an event in Stockholm with Eric Meyer? So, yeah, of course. So they had, so Jimmy Nilsson, the CEO of Factor 10, he talked to Eric asked Eric to do a talk at Focafé Stockholm. And Eric said, yeah, of course, super. That was not a hard question. No, that's what I see.
Explain to you tonight, like after the talk, you should feel that everything I said was trivial. Okay, if you feel like that, then I've done my job. If it doesn't sound trivial, then I've not done my job. All right, so I'm going to take this concept and really boil it down to the simple essence, and hopefully you will agree afterwards that it is in fact trivial. Like when I was an academic long time ago, I was teaching software engineering. I don't know if people here ever read Somerville, the software engineering book. I was teaching this from the first edition. And when I was doing that, I felt like a vegetarian butcher. So I felt like, I'm teaching these students how to do large-scale development, but I have no clue how that works. I never did it myself, so I cannot teach this thing and look at myself in the mirror seriously. So that's where I quit academia and went to industry. And maybe fortunately, I don't know for me, but every place where I've worked at, and maybe it's the self-selecting bias, this was the main software engineering principle that we applied. And again, it's another quote from a famous president, working software over following a plan. So everything in software engineering you can forget. It's all about creating working software, right? And what that means is that software is the currency. Software is what it's all about, or code is what it's all about, right? And then how do you create code? Well, you author it, you generate it, you search for it, you synthesize it. And then when you have code, you edit it and you refactor it. And then you get ultimately, of course, the goal of code is to run it in production. So you have to deploy and save it in source control that you can find it back. But here's the question. It's after so many years, 50 years ago, there was a famous conference where the word software engineering was invented, and also the word software crisis. Software yet in our heads, we don't know how to write software. So maybe it's time that humans stop writing software and we leave it to the machines, because we as humans are maybe not smart enough to write software. So that's what I decided to do. It's okay, I accept I'm just a human, I'm stupid, I'm not going to try to write software anymore. Can we teach the machines to do it for us? And again, if you look anywhere else in the real world, machines are doing the work for us. We're not digging holes by hand. No, we have a machine do it for us, and et cetera, et cetera. So that's what we're going to do. Okay, and of course I'm not the only one that wants to do this. This is what people call software 2.0. So everybody here is probably still doing software 1.0, where humans write the software. In software 2.0, it's the machines that write the software. All right. This, by the way, is an interesting blog post that you should read. So what's the difference in really concisely expressed between software 1.0 and software 2.0? Software 1.0, there's a human that takes coffee and turns that into code, or beer, or wine, or chips, peanuts, whatever more do I see. In this new world, a model. Now, what's the difference between model and code? So I think the machine learning people like to use expensive words, and the whole point of this talk is to show that all these expensive words are trivial. Remember that. But there's a big difference between model and code. You can say model is just code, but there's one difference. Machine learning people are less arrogant than programmers. They acknowledge that these models don't compute precise results. They predict a result. Where if we write a function and we say it's a function from end to end, we promise a lot of things. We're over-promise, but we under-deliver. Because this function might have bugs, it might throw exceptions, it might fail. And when you look at the model, it just says, oh, this is here's a picture. This is a cat with 80% probability and a dog with 10% probability and a glass of red wine with like 2% probability. So it's just honest about the fact that it's just guessing. And I think this is a good thing in general. So I think even in software 1.0, we should be like less arrogant and say, yes, these things might go wrong, or we're just guessing. And I think that's what probabilistic programming is a good thing for, because there you can return probability distributions that express the uncertainty or the certainty about the results. So this is a big kind of difference. The other difference is that the new currency, or what people say that data is the new currency, or data is the new oil, right? So data is what drives the machine learning. So how do you get the data? Well, you get that from tracing or monitoring or other things. And then just like you have to refactor your code to clean it up, you have to clean up your data. And then once you have your data, you can use it to train your model or to visualize it or do other things with it. And some people say that, like, this part here is like 99% of the work, and maybe the cleaning is like 80% of the work. And so there's still like a lot of like human work involved. But ultimately, once we have the data, we can train these models. So it's really the magic is in that training data, because the machine learning model cannot. It's like, again, like we talked a little bit about this before. I don't believe in artificial intelligence. These things are not intelligence. They just get like generalized from the data feeds to it. Maybe other people believe in AI. It's not me. It's a useful tool where I can have the machines generate models for me, but I don't pretend that it's intelligent. Here is a example. This is the hello world of machine learning. It takes flowers with some features, characteristics of these flowers, and then it tries to predict what flower it is. Now, again, it tries to predict what flower it is. So this is like this bar chart here is a probability distribution. So for this flower, it thinks like, that is whatever, Setosa, I don't know. But you see that it thinks it's that one, and maybe you got like, with a lower probability is one of the other ones. And then for the second flower, it thinks that's like pretty sure that it's this one. And for the last one, it's got like, yeah, okay, I think it's that one, but these other ones are also kind of possible. Okay, so this is the big difference between, like, a regular programmer would say, oh, I'm so smart, I know exactly that it's this flower, and you don't express the certainty or uncertainty. So I think this is one of the things, like, if you forget everything I say today, this is one thing that we can learn from machine learning, is that, think in terms of your answers as being uncertain, right? And so express that. So you should never claim an overpromise, like, I'm going to give you a precise answer when it's not precise. Now the other thing is that if I would give you 10 million Swedish kroner to write a program like this that can recognize flowers based on some features in the traditional way, you couldn't write that. Even Jimmy's 10x developers, cannot do that, right? Even if they're 100x smarter, they cannot do that. You cannot beat machine learning with these things, right? Everybody uses their smartphones, like, whenever you take a picture and it shows, like, little squares over people's heads, that's using machine learning. You cannot beat that with traditional algorithms. So there's a whole bunch of things that, even if you don't believe in machine learning, there's a whole bunch of algorithms or applications that you can access in this new world, in the software 2.0 world, that you couldn't do in the traditional world. So that's another reason to look at machine learning. And even if you're skeptical about it, it just opens up a whole bunch of things that we couldn't do before. And that's, for me, the main reason that I'm interested. So here's another example, recognizing cats and dogs, which is obviously super important, right? We all know it. We cannot live without that. And as I said, like, even though software engineering is 50 years old, we don't know how to write programs like that. So how do we write programs like that? Well, let's look how we do that. So this is the high-level explanation of what machine learning does. So you got, like, you write your model here, which really is a composition of functions. And the machine learning people, and when I say machine learning here, I typically mean deep learning. They say, oh, it's like, I have a bunch of layers. These layers are just functions. And if you stick two layers together, you're doing function composition. So what you're writing, the model that you write, is a composition of functions that is parameterized by weights. And now what you're trying to do is you're feeding the input to this function, and out comes a guess, because that's what this the machine learning algorithm does. You look at the output that you get from your training data, and then you're applying a loss function that kind of compares how far these two answers are, what the difference is in these answers. And that's the error. And then what you do is, like, you apply some high school mathematics. Like we all know from high school. Oh, is this me or is this? Oh, it's a ventilation. I thought it was like, like the feedback. But the ventilation, that's a great sound for ventilation. It's like a rock stadium. Yep. But we all know from high school, if you want to get, like, minimize a function, right? Say that you just have a simple quadratic function. How do you minimize that? Well, you take the derivative and you look where the derivative is 0. Okay, so what do we do here? We take the derivative of the loss function here, and we look, is it got, like, if it's positive, it means we have to move a little bit to the left. If it's negative, we have to move a little bit to the right. So that's what we're doing here. We're kind of updating these weights, and we're rinsing and repeating that until we got, like, set these values. So here's some actual code that shows kind of like what you actually have to do. And again, this is the hello world of machine learning. Here is the training data. You have to specify your weights. here is the model. And again, like, these are, I'm not going to get like explain this here, just get like putting together usually some standard layers with some transfer functions and whatever. And then what you need to do is you need to map your discrete values, in this case flowers, to a kind of like continuous input. And this is like, I think one of the still open issues in machine learning, because since these, I should go back to here, why I'm interested in differentiable programming, because in order to get like, be able to get like, up these weights based on the derivative, taking the derivative here, these functions have to be differentiable. And so what we're trying to do is we're trying to define a programming language in which we can write that yellow box, where every function, and these are functions, these are really pure functions. So if functional programming wins, it is because, it's used in deep learning, not because people are using Scala or Haskell or whatever. No, this is where functional programming is useful. But we want this functional programming, or functional program, where every program that you write is differentiable, such that you can plug here in arbitrary, an arbitrary function as long as it's differentiable. So this is what, what people get, mean when they talk about differentiable programming, is that you can, instead of having like just layers, I can put much more complicated things in that yellow box. But you still now have to map from your discrete space into this continuous space. And the problem of embedding is really hard. In this case, it's simple because all these values are already got floating point numbers. But in general, people do get like all kind of crazy tricks to map from discrete space into continuous space. In some sense, that's not a new thing, because we have the same thing with databases, right? This is called the impedance mismatch. If you have a relational database and you have your Java objects, now you have something that has hierarchy and inheritance, and here you have something that has flat tables, and people have figured out over the years how to do these mappings. There's patterns. Here we're not yet that far, but I'm pretty sure that over time we will have best practices how to map complicated things into this continuous space. But this is something where there's the dot dot dots. This is something you have to define. All right, so let's just assume that we know how to get do all the mechanics here, where we just adjust the weights. And what I want to get focus on in this talk is how can we get differentiate arbitrary code, or how can we get make sure that if we write a function that is differentiable. And if you get do a little Google search for this, you find a lot of explanations for this, but these are really complicated. Okay, so they use expensive words like strict, symmetrical, monoidal categories. I'm already I need they don't have anything stronger here, but when I see this, I need something stronger. Or here it's again the simple essence of automatic differentiation. Oh, that also uses category theory. And here's automatic differentiation in machine learning. Oh, this talks about Jacobians, and look at all these Greek letters, and I don't even know how to type this on my keyboard, and how do I put a dot on top of something, boldface? It's just all too complicated, right? So can we explain this without any math, with only high school math or even elementary school math? So that's my claim. You don't need any of this, okay? So what is the real essence of automatic differentiation? Because my brain is the size of a peanut, and there's a whole bowl of peanuts. Can you pass that bowl of peanuts there? So these are peanuts. This is the size of my brain. So just to make sure. So it has to be simple, because otherwise it just doesn't fit. There's not many neurons that fit in this little volume. Okay, so let's make it really simple. And hopefully what you will agree with me afterwards is that it's like a dog, right? You have this beautiful dog. It looks very impressive. You put the garden hose at it, and then underneath there's a really simple skinny dog that's not at all kind of scary. And this is the same thing here. So you look at this stuff and you think, oh, do I really need to understand all this? No, you don't. So let's put the garden hose on all this stuff and see how easy it is. This is all the math that you need. Okay, this was invented by William Clifford in somewhere 100 years ago, 200 years ago. Cannot even do simple arithmetic. So everybody knows complex numbers, right? You remember complex numbers from math? If you're doing graphics, you're probably using complex numbers all the time. So complex number is a plus bi, where I squared equals -1. Yep, remember that? Then you think, why I squared equals -1? Isn't that weird? Sure, but it's okay, right? You can just take it. But why can't we just take another? Why can't we define I squared to be +1 or 0? So let's do that. So a dual number is like a complex number, but instead of I squared equals -1, we say I squared equals 0. And in order to distinguish between complex numbers with I and dual numbers, we just use a different symbol. So we use epsilon instead of I. Okay? So a dual number is like a complex number, except I squared epsilon squared equals 0. Now that choice is really remarkable, because if you do that, this follows. If you have a function f and you apply it to one of those dual numbers, what it computes, it computes f of a plus the derivative of f of a times b epsilon. And again, this is like a magical property. Don't care how this works, we will profit from it, right? We'll just take it. Just if this is the case, I'll take it, right? Now, if you want to understand why this is the case, you have to look a little bit deeper. And you have to look at Taylor expansion. Maybe you remember Taylor expansion, Taylor series from math. This is really remarkable, right? Somebody in, like, Mr. Taylor in 1715.
Growing a startup is tough. You have limited resources and a lot to do. You're thinking about how to best apply your team's time, maintain infrastructure, or build custom tooling.
I don't know how you can come up with this, but he kind of said, like, if you give me a function, you can forget a little bit about the a. If you give me a function f, I can write it as this infinite sequence, this infinite sum that involves factorials and the nth derivatives and like exponentials. It's just mind-blowing. So this is the mind-blowing math that's behind this. But again, like from this, you can show here that when you take epsilon squared equals 0, that if you apply a function to a dual number, it will give you the function plus the derivative, right? And this is all the math that we will use tonight, plus some regular functional programming tricks. Okay, so that looks much less scary than all this category theory, strict monoidal categories. It's just like simple math from 1715. I mean, how, like, I don't know, probably Stockholm, or they already built like beautiful homes back then. Anyway, if you look at this thing, that if you take a function on numbers and you lift it to work on dual numbers, and that thing is a functor. So, but again, I promise that I won't use expensive words tonight, so you can forget that. But I thought there were a couple of, like, somebody told me, oh, I learned monads from you. I think it was you. Well, here's like, this is a functor. But that's all kind of like, expensive stuff that I will do tonight, just for you. Okay. Now you can go home and say, I know that dual numbers are like lifting into dual numbers is a functor. That may impress your colleagues at work tomorrow. Now let's simplify it even further, right? Because just this a plus b epsilon, that's really just a complicated way of writing a pair. So let's just write it as a pair and then show the math. So if I have two of these pairs and I add them up, what I do is I just add up these guys and I take the derivative of these things, and that's it. If you multiply two of these pairs, you get this here. And if you look in Wikipedia for the product rule of differentiation, that's what you find. This is the product rule of differentiation, and it follows directly from dual numbers. And then again, remember, this was a property that we got, like, that we're interested in. And there's no epsilon here because we're just doing pairs here. Notice that we don't need a chain rule. I don't mention the chain rule. I don't know if you remember the chain rule. That's something I can never recall. I always have to go to Wikipedia to look at how the chain rule works, but you don't need it, as I promised. This is the only math you need. If you do it, this follows from that. All right, so let's write it in code. So I showed it in handwriting. Now let's write in code. So here's some Scala that implements dual numbers, and it's exactly as I promised you. It's just a pair of the real part and the epsilon part, and then you define addition, multiplication, just for fun. I also define division and sine and cosine, and then here's implicit conversion from doubles to dual numbers, and that's all. So here you have automatic differentiation in, what is it, 10 lines of code? How hard is this? Right? No category theory. Yes, it's a functor, but it's only relevant for you. All the rest is like, what is a functor? It's really easy. So life is sweet. This is math from 1715. So let's look at some examples. So here's, a function. It's like x squared plus 2x plus 3. We can take the derivative of that. Here's a more complicated function that uses assignments and loops and everything. It computes the sine function using Taylor expansion. Does it matter if this thing takes a dual number and returns a dual number? I can take the derivative because that's what dual numbers compute. And then here, this thing computes x times x times x times x times x times x. It's like, as a graph. So it's kind of sharing. And that works as well. If I run that, you see that thanks to the magic of the JVM, they should be linear. But thanks to the magic of JVM, the longer this thing is, the faster it goes. Isn't that amazing? These modern machines are awesome, right? It's like, instead of like performance going like this, it goes like this. I don't know why it works, but like, I'll take it. So I think here's probably got, like, switching from, like, one generation to the other. I don't know what happens, but this is why people prefer C++ over a garbage collected language, because like in C++ you have like a predictable curve instead of like all these spikes that your garbage collector like messes you up. Which is also strange, right? It's like 2018 and we still have not built a predictable garbage collectors, and you get strange graphs like this. All right, now. Of course, I also want to take derivatives of functions with multiple arguments, because if you remember the very simple neural net that I showed you had multiple weights. So, and all these weights I want to take the derivatives with respect to all these weights. So I need to take derivative of what people call multivariate functions. So you can go tomorrow if you got like
Hey guys, welcome back. Video generates a computation graph for you, and basically
Differentiation is everywhere in science and engineering. In machine learning, we need derivatives when we use gradient-based optimization. For example, in gradient descent, where we attempt to minimize some objective function by repeatedly tuning our model's parameters in the direction of the negative gradient. In this video, we'll try to understand the basic idea behind automatic differentiation, or autodiff, a set of techniques that allow us to compute derivatives efficiently. It'll help if we first contrast autodiff with some other ways of computing derivatives. One way, what we might think to do from high school calculus, is to look at our function and manually differentiate it using our basic derivative rules. We could simply code up the result and call it a day. But this can be a fairly tedious process for more complicated functions. We generally prefer an automated approach. Now, automatic differentiation, as its name suggests, is one of these, but it's not the only one. Another is numerical differentiation, which uses the method of finite differences to approximate derivatives. The simplest version intuitively follows from the limit definition of the derivative. Say we have a scalar-valued function f. For a partial derivative with respect to xi, we set up a quotient where in the numerator, we subtract two evaluations of the function at nearby points, x plus hei and x. Ei is just the unit vector along the ith axis, and h is a step size, typically a small fraction. So while this can be fairly simple to implement, some issues come up with accuracy and numerical stability. One issue is truncation error. We're trying to approximate a limit as h goes to 0, but we're using some non-zero h. What we're really calculating is the slope of a secant line near the tangent line of x. As h gets closer to 0, and the secant line approaches the tangent line, the truncation error decreases. But this eventually leads to what's called rounding error due to the limited precision of floating point arithmetic. So we have to carefully consider this trade-off between truncation and rounding error when selecting a step size. Now, in machine learning, especially in the context of, say, training neural networks, some approximation error may be okay. After all, stochastic gradient descent only uses a noisy estimation of the true gradient. The bigger problem with numerical differentiation here is that we need O of n evaluations for an n-dimensional gradient. This time complexity simply won't cut it when we have a model with millions of parameters. Another approach is symbolic differentiation, which is essentially an automated version of the manual differentiation we looked at before. We hand a closed-form version of our function to a symbolic differentiation program that applies the standard derivative rules, transforming the original expression into the derivative of interest. This bypasses the sources of error we saw in numerical differentiation, allowing exact computation of derivatives up to numerical precision. But it comes with its own difficulties. One problem is known as expression swell, where derivative expressions may be exponentially longer than the original function. Why does this happen? Well, some derivative rules, like say the product rule, naturally lead to duplicated computation. Any computation shared between f and f prime here will be executed twice. If f itself involved a product of functions, this would be further exacerbated. For example, let's look at this recurrence relation known as the logistic map. For n equals 1 and 2, the derivative expression is about as simple as the original. But as we increase n further, the derivative quickly gets out of hand. Now, in this example, we can simplify the expression quite a bit to polynomial form, but this isn't always possible. Consider this function known as soft ReLU, a common activation function in neural networks. Even two of these composed together leads to a fairly involved derivative. Symbolically differentiating through a network with many layers is usually not tenable. In addition, symbolic differentiation requires our function to be expressed in closed form, limiting our ability to use control flow mechanisms like conditionals, loops, and recursion. Automatic differentiation computes derivatives with the same accuracy as symbolic, but operates directly on the program of interest. Rather than produce an expression for a derivative, the sole intent of autodiff is to obtain its numerical value. It bypasses symbolic inefficiency by leveraging intermediate variables present in the original function's implementation and more easily handles control flow. The basic idea is that, ultimately, implemented differentiable functions are composed of underlying primitive operations whose derivatives we know, and the chain rule allows us to compose these together. There are two main versions of autodiff, forward mode and reverse mode. We'll first take a look at forward mode, the conceptually simpler of the two. Forward autodiff involves augmenting each intermediate variable during evaluation of a function with its derivative. So instead of individual floating point values flowing through a function, we can think of these as being replaced by tuples of the original intermediate values, also called primals, paired with their derivatives, also known as tangents. Say we're interested in this function. We have two scalar inputs, x1 and x2, and a single scalar output. We notice some repeated use of certain sub-expressions, which would likely influence how we implement it. We start with our two input variables, which we'll denote with v-1 and v0. As we proceed, we evaluate intermediate variables, some of which will be used more than once in later computations, and we eventually reach the final function output. Now, suppose we'd like to compute the partial derivative of this function with respect to x1, at the point x1 equals 1.5 and x2 equals 0.5. In addition to computation of the primals, we simultaneously compute their tangent values. That is, each evaluation of an intermediate variable, vi, will now be accompanied by the value of partial vi, partial x1. A single pass through the function now produces not only the original output, but the partial derivative of interest. This example function only has a single scalar output. Suppose it had multiple. Forward mode autodiff allows us to compute the partial derivatives of each of these outputs with respect to an input variable, all in a single forward pass, which is great. The catch is that we have to run a separate forward pass for each input variable of interest. For this example function, we'd have to follow the same procedure again to get partials with respect to x2. Consider general functions from Rn to Rm. Each pass of forward mode autodiff produces one column of the corresponding Jacobian. This starts to give us a hint about when we might like to use forward mode. We'll see that, relative to reverse mode, forward mode is generally preferred for computing Jacobians where n is much less than m. That is, we have few inputs and many outputs. Notice in our example that we initialized x dot to 1, 0, since we wanted the partial derivative with respect to x1. But partial derivatives are just the axis-aligned special case of more general directional derivatives. We can initialize x dot to any unit vector we'd like, and compute the corresponding directional derivative with a single forward pass. More generally, we can actually compute Jacobian vector products without ever computing the Jacobian matrix itself. We set x dot to the vector of interest, and proceed with forward mode autodiff. Now, this seems a little weird, right? After all, we just said that forward mode requires one pass through the function for each input. Well, we can basically think of the Jacobian vector product as just the Jacobian of a different function, the composition of our original function, and one with a single scalar input whose Jacobian is the column vector r. Because the overall Jacobian of this composed function now only has one column, we see why a single forward pass is sufficient. There are several ways to go about actually implementing forward mode autodiff. One route, perhaps the simplest to implement, is to leverage operator overloading, where we abstract away the actual derivative computation. Instead of operating on raw floats, we write a simple class with attributes denoting the values of both the primal and its tangent. We could then overload the primitive arithmetic operations to additionally handle derivative computation. For example, for the addition operation, we typically just take the two raw values and add them together. Instead, we'll include the simple sum rule for derivatives and set the dot attribute of the returned object accordingly. We would do the same for the other operators, allowing us to implement the overall function just as we normally would, except this time the values of both the original function and its derivative are produced. Another general route is known as source code transformation, where input source code is actually manipulated to produce a new function. This can be more efficient than operator overloading, as it directly exposes the logic of the new source code to the compiler, but it's a bit more difficult to implement. I'll provide links in the description for further details about different kinds of implementations as well as example software libraries. Now, we saw that forward mode autodiff looks like a good route when there are only a few inputs that we're interested in partial derivatives for. But in the context of machine learning, we usually don't meet this condition. In fact, we're typically in the scenario where we have a model with many parameters, even numbering into the billions these days, and we'd like the gradient of a scalar loss with respect to these parameters. Reverse mode autodiff allows us to handle this case efficiently. Rather than propagating derivatives forward, they'll be propagated backwards from the output. This is carried out in a two-part process. We first start with a forward pass through the function, evaluating intermediate variables as we did before. But instead of simultaneously computing derivatives, we store the dependencies of the expression tree in memory. Then, after completion of the forward pass, we compute partial derivatives of the output with respect to the intermediate variables, quantities known as adjoints, which we'll denote with v bar. To obtain the adjoint v bar I for a particular node, we look at each of the node's children, multiply the adjoint of the child by the partial derivative of the child with respect to vi, and then take the sum of these products. So vi's contribution to the final output is determined both by how each of its children affect the output and how it affects each of its children. At the end, we obtain partial derivatives with respect to each input. So the gradient is computed with just a single execution of reverse mode autodiff, making it far better suited to the typical optimization setting in machine learning. In the context of neural networks, the backpropagation algorithm, which is used to compute derivatives with respect to network weights, may be viewed as a special case of reverse mode autodiff, where the adjoints with respect to intermediate layer activations are propagated backwards through the network. For general vector-valued functions, reverse mode produces one row of the Jacobian at a time, making it ideal when we have few outputs relative to inputs. Now, for both forward and reverse mode, what's especially neat is that a single pass does not take much longer than evaluating the function itself. In fact, computing a single column of the Jacobian in forward mode, or a single row in reverse mode, is guaranteed to take less than 6 times the number of operations in the original function implementation. In practice, it tends to only be about 2 or 3 times. Reverse mode is usually a bit more memory intensive than forward. We have to store the values of intermediate variables and their dependencies in memory. Various techniques have been developed that help make this more efficient, including rematerialization, where only a subset are stored and the remainder are recomputed during the backwards pass. Forward and reverse mode are the two extremes of automatic differentiation, but in some settings a hybrid approach is actually preferred. For example, in second-order optimization, where information about an objective function's curvature is taken into account, a Hessian vector product is sometimes needed. A reverse-on-forward version of autodiff allows efficient computation of this product. First, we use forward mode to compute the directional derivative gradient f times v by setting x dot to v, as we did before. Then, reverse mode is used to differentiate again, resulting in the Hessian times v. As with the Jacobian vector product, we're able to compute the Hessian vector product without explicitly computing the Hessian matrix itself. In general, we can compute arbitrarily higher-order derivatives by composing multiple executions of autodiff together. So, automatic differentiation helps make life much easier when we need to obtain derivatives of complicated functions. It's not always applicable, But when we can directly implement a function of interest in code, this set of techniques allows accurate computation of its derivatives with minimal overhead. AutoDiff has a rich history, and ongoing research continues to improve it. Check out the links in the description to learn more. Thanks for watching.
Create effective marketing campaigns in minutes. MailChimp's AI auto.
If you've coded in Python before, you've probably come across the main Python libraries. Two of the biggest examples, of course, being NumPy and SciPy. These examples are used extensively in the scientific community, and for a good reason. They provide many important functions that are used all the time in scientific research. But compared to what we're about to explore, they're nothing. With the right tools, you can take a simulation of 400 particles and turn it into a simulation of 10,000 particles, but at no extra time cost. The secret, of course, is proper utilization of computer hardware, and more specifically, the GPU, which most people have access to these days. Welcome to the second episode of the Python GPU series, the Schrödinger equation. So like before, I have my old CPU code on the right-hand side here and my new GPU optimized code on the left-hand side here. And so the old CPU code in this video actually corresponds to, I think it's my 6th video ever, where I solved the Schrödinger equation in 2 dimensions. Of course, in this video, we have access to the GPU. We can add another dimension and solve it in 3 dimensions. So the first thing we'll do is we'll solve the Schrödinger equation in 2D using both techniques, and I'll show that the GPU method is quite a bit faster. And given that it's faster in 2 dimensions, we'll then move to 3 dimensions and solve the hydrogen potential. So of course, this can be solved analytically, by the way. Any quantum mechanical textbook goes through solving the 3D hydrogen atom potential, but we'll solve it numerically on a computer here. And of course, the advantage is that we'll define the particular hydrogen atom potential here, but when you're doing something numerically, you can define any potential you want. So if you want to come and take this code, link in the GitHub, you can add a different potential, something like the helium atom, where the protons are spaced apart, and then what do the eigenstates look like? So we'll import code in both cases here. And so the first thing we want to do, of course, when we're solving for the 2D Schrödinger equation, again, we're solving for a 2D wave function to start. So there's going to be x coordinates and y coordinates. So the smart thing to do in both cases, and the code, as you see, is exactly the same here, is we're just going to create a mesh grid of x and y. So there'll be 400 points, and we'll make an mesh grid. And this, by the way, is a short notation for the NumPy mesh grid. So it says go from 0 to 1. So we're going to go 0 to 1 in x, 0 to 1 in y. And we're going to use n points here. And actually, for some reason, with the short notation, you have to multiply
I'm Dan, and I'm colleagues. At that time, like animations, it was always in matrices and frames.
F and its derivative, combines them into one, but now we wrap it up with a D. So this is just a little bit of just programming language wrapping. So all I did is but we also get a derivative there. But we also const F, where const is the what this looks like operationally. So for instance, so this is the one that says if F is a linear function, okay, then the differentiable form, D, is a function that takes A and gives you F of A and then A. I could have written that differently as just F fork const F, where const is the thing that whatever argument you give, it gives you F back. All right. So for instance, if you look at how composition works, there's really two things in here, because we said the meaning of the specification D hat is we're going to have the original function
All right, agree with client and start time tracking. Great. So for Q4, I was thinking.
What are you doing?
Oh,
In the previous lecture, we learned that we can always trace back the origin of an U6. So as input was the multiple single P without and from the two outputs, you can see it said two outputs plus the fee. So from the two outputs, one output is already.
Next, I want to talk about Bitcoin by the nonce field in the SOC. So the project comprises 6 wrapper in the system. To this pattern. My design uses 32 digesters due to resource limitations. So an output every other clock cycle at a clock rate of 80 megahertz gives a hash rate of 40 megahashes per second, which is what we saw in the beginning of this video. So that's the end of my explanation of the Bitcoin miner. Hopefully it was at least mildly interesting.
In this module, I'm going to briefly introduce the idea of differentiable programming. And differential programming kind of just runs off with ideas of the computation graphs and backpropagation that we develop for simple neural networks. There's really enough to say here to fill up an entire course at least. So I'm going to try to keep things pretty high level, but I will try to highlight the power of composition. So differential programming is closely related in general. You can pool layers, and also actually we first have to embed them into a sequence of vectors, and then it takes in a collection of vectors, of input vectors and a query vector, and then outputs a single vector. And intuitively, what the attention is doing is it's going to process y by comparing it to each of these x's. Okay. So mathematically, what this is doing is you start with
What's the first thing you do when you wake up in the morning? If you're checking your phone, stop that. Instead, try this technique.
Now let's say if you're given the graph of f of x, and it looks something like this. If that's f of x, what is the graph of f prime, the first derivative of f? How would you graph it? Well, for one thing, if you know the parent function, it can be easy to find f prime. For example, the parent function for this graph is x squared. So that's f of x. The derivative of x squared is 2x. And so we should have the derivative is basically a linear function with a slope of 2. So it looks something like that. Now, let's analyze the slope of f, because the derivative gives you the slope is so increasing. We need the second derivative. How can we graph that particular function? Slope is 0. So at that point, the y value has to be 0, which means that it must be, so the slope is positive. Notice that the slope is never negative. The function is never decreasing. And as you can see, find f prime and f, the function that we have. Therefore, f prime is going to look something like this. It's going to be an upward parabola. And the derivative of, and now let's analyze it. And then we have a horizontal tangent, slope is positive, the x-axis. So the derivative of the function is, so let's, of f prime of x. This time we don't know what, and a function becomes such as the x-axis. -1, beyond 3, it's increasing, beyond, so -1 back to negative, and then it's now between increasing, so zeros after that. But it helps. So let's try another example. Let's start over. So beyond -2, the y value will be 0. Between -1 and 1, it will be 0. It will be 0 as well, at a constant rate. Because on the left side, the slope is -1. And on the right side, the slope is +1, and it's constant. So we're going to have a horizontal line. So that's how you can graph the derivative of the absolute value function.
Let's start with quantum deep learning. So this may feel like a bunch of buzzwords smashed together, but really the idea I want you to take home here is that you can think of quantum circuits and quantum algorithms as objects which you can train and optimize using the exact same tools that you would use to train and optimize a neural network or a deep learning model. So as point of reference, what is deep learning? It's a subfield of machine learning that originally grew out of the study of objects called neural networks. So as an idea, we could say the following. Let's build machine learning models out of composable differentiable functions. That's a very high-level summary of what deep learning means. So in particular, those composable differentiable functions are originally neural networks. And a neural network has the following structure. It's a function f, which takes an input x and has 3 parameters theta. And what you do is you take that input x and you multiply it by one subset of those 3 parameters, which is called a weight matrix w. And then you add in another subset of those 3 parameters called a bias vector. And then you take the result of that and you put it through what's called an activation function sigma. And this is a differentiable transform, and it's also composable. And that's how you get multi-layer software for differentiable programming. These things you might have just assumed are used for machine learning, but they're extending more and more to a predictor, to classify whether you have a particular object in your image, and then you, but it's arbitrary code. Again, you want to define, and after optimization, this code should now be very well tuned to specific purposes, which may go beyond what a machine learning model is meant to do, which is usually to make predict configuration here, a peace sign, you can see. Differentiable programming is quite broad. There's a lot of ideas now starting to emerge that are maybe less aligned as deep learning and more aligned as differentiable programming.
So I just list a few here. Neural Turing machine, this is basically a neural network type model that has access to an external memory. There is neural ordinary differential equations where you're not optimizing a neural network, but you're optimizing a solver to a differential equation. Other things like physics or graphic engines. And as well, you might have seen this Deep Dream a few years ago. And this is actually something that inspired me to get into machine learning. The idea here is that you have already trained a predictor, to classify whether you have a particular object in your image, and then you take the input image then as your trainable object, as your object that can be optimized, and you freeze the predictor's weights, you freeze the predictor's training, and you just train the input. And you can say, give me the image that looks most like towers, or has the most towers in it, or best represents towers, or best activates the tower classification. And you end up with these really weird, crazy images. And this is starting to bleed out of neural networks and more into differentiable programming, where the thing you're optimizing is no longer a model, but the thing you're optimizing is the image itself. So there's very friendly software for differentiable programming. These things you might have just assumed are used for machine learning, but they're extending more and more to broader things. And there's covering Python typically, but also Julia libraries. And the very nice thing that these libraries do for you is something called automatic differentiation. These handle all the optimization parts for you. So you can build your computation, you can build your program, and then these take care of training it for you, in particular computing the gradients. So now we're talking about quantum computing. We want to connect that to deep learning. So very basically, quantum computing, you have a set of quantum systems which are manipulated by a series of gates. We call this a quantum circuit. And the power of quantum computing comes from its inherent special ability to interfere complex amplitudes in a very high dimensional space. So it's not just the ability to work in a high dimensional space, but it's actually the ability to do interference in that space. Now, the basic structure of a quantum circuit is you start with some initial state, psi. Typically, this is an all-zero state or a ground state. Then you execute some particular unitary transformation, call it U. And U can be broken down into a sequence of individual gates. And this is the bulk of your circuit. And then at the final step, you measure some observable quantity. It's called B. And this is the step that your quantum state is converted into classical information, which is the measurement result. So the key point I want to emphasize about quantum circuits is that if you look at the average value of your measurement results, this is also called the expectation value in quantum theory. If you look at the expectation value of your results of measuring the observable B, then there's this nice formula called the Born rule, which tells you exactly what that looks like mathematically. And it basically is just an inner product of two vectors, or a product of matrices and vectors. So psi, if you're not familiar with the notation, psi in these, it's called a ket, and it's just a vector. And then U, parameterized by theta, U is a matrix, and it's just multiplying that vector. B, again, is represented as a matrix. It just multiplies the thing to its right. U dagger is the adjoint gate, or the adjoint unitary of U, so like the complex transpose. And then finally, you have, again, it's psi, but the direction is reversed, and this is now a dual vector. So in the end, this is just a kind of inner product, and it gives you a scalar value. And it's a very nice formula. But it's all just linear algebra in a very high dimensional space. Now, the important point I want to emphasize is I put this value theta in for the unitary transformation. So what that means is that the final expectation value is a function of theta, which are the gate parameters. And it's a continuous function as well, since it's just linear algebra. So this allows us to start thinking about quantum differentiable programming. As I said on the previous slide, the Born rule is just a linear algebraic expression, so it's differentiable, which means that all the ideas of differentiable programming that we should be able to train an object using gradient descent, all this applies to quantum circuits that are parameterized unitaries. So we have a circuit, and it spits out some function which depends continuously on parameters theta. And we should be able to train that function just like we would train a neural network. So this is cool because it opens up some possibilities for how you can connect quantum computing devices with machine learning. One perspective is to use quantum devices for machine learning. So you use a quantum device as to make a classifier or something. The other way you can think of it is actually to use machine learning tools and differentiable programming tools to better understand quantum systems and quantum computing. So this is what I would call the machine learning for quantum perspective. You're using the tools of machine learning and you're applying them to quantum computing circuits. So this is kind of a duplicate of the slide that I showed earlier, but now it's how can quantum machine learning be successful rather than how deep learning was successful. So it's a really cool point right now because we're starting to see those hardware advancements. We have devices which are getting harder and harder to simulate and are doing more and more interesting things. As I'll get to a bit later, we do actually have also some workhorse algorithms we can rely on, and these can be largely ported over from deep learning. And as well, there's an emerging suite of software devoted to quantum machine learning and differentiable programming of quantum computations. So one thing is Penny Lane, which is done by my team at Xanadu, but also we have TensorFlow Quantum, we have a Julia library called YAO, and there's a library developed by a University of Toronto group called Tequila. And they're all focusing on this core idea that quantum computations are differentiable programs. So that's the story so far. It's pretty cool. It says that the ideas of deep learning are very nicely ported over to quantum circuits. But there's still a missing piece of the story that I haven't really explained yet, which is if we want to train quantum computers like neural networks, we want to use gradient descent, we need a way to compute the gradient. But as I said, quantum computers have this special capability of interfering complex amplitudes in large dimensional spaces, which is in a lot of cases hard to simulate or emulate classically, or basically intractable to do so. So if we have a computation, we have a circuit that is intractable to evaluate on a classical device, how could we possibly compute the gradient of that? So we not only need to evaluate the function that's coming from the circuit, we need to evaluate the gradient of that function. How can we do that if the circuit itself is classically intractable?
This is how AI optimizes my schedule. So I have a project coming up, so I start by listing the project and then setting.
Let's explore how we can compute the gradients of quantum circuits automatically using the parameter shift rule. So as a summary of the story so far, there's this idea of differentiable programming where we want to write code which is numerical in nature and differentiable in nature, and then optimize it towards some particular goal. We can also recognize that quantum computations are differentiable. So this means that we can apply all the tools and machinery from differentiable programming or from deep learning to quantum circuits. In particular, if we can compute the gradient of a quantum circuit's output with respect to the circuit's parameters, we can then update those parameters iteratively using a gradient descent strategy and train the quantum circuit to do something interesting. So our first worry is, how do we actually compute the gradient of a quantum circuit? The interesting circuits are likely going to be very intractable. So how could we possibly compute the gradient of those circuits? So a few strategies can be proposed. One thing you could say is, let's not compute the gradient, let's just approximate it using some agnostic method like a finite difference estimator. Another thing you could do is say, let's just do everything classically. Let's write a simulator of our circuit classically and use machine learning tools that are classically available to compute the gradients automatically. Or you could say, maybe this is too much trouble. Maybe we should just avoid using gradient descent and we should try some other optimization strategy. So I would say all of these approaches have some undesirable elements. So for instance, for the finite difference method, it could work, but you're then making an approximation. And there are other sources of approximation or imprecision in quantum computing that would then compound on top of that. In particular, the device noise of near-term devices could influence your approximation quality. For the second method, this is actually a strategy you can use, but it only applies to small quantum circuits. It's not going to work when the circuits are any significant size. And the third approach would be to use a different optimization strategy. And I would say we definitely could do that, but then we might be flying blind. We might have to reinvent the wheel. Whereas if we can find ways to compute gradients, we can use all the tools and machinery available from deep learning. So in order to figure out how to actually compute the gradient of a quantum circuit, I'll take a simple motivating example. Suppose someone gives you a computing device which is able to do one thing and one thing only. And that is, if you give it the value theta, it's able to compute sine of theta.
But we're just becoming more reliant on...
That gives us a method for evaluating this particular function. But what if we want to evaluate its derivative? Right? As I said, this function, this computing device only does one thing, evaluate that single function. The derivative of sine is cosine, and cosine is a different function from sine. However, cosine does have the interesting property that it looks like a sine, but with a phase shift. So it turns out that, I'll write it here in a bit more general form, but functions like sine or evaluating this particular derivative can always be expressed as a forward shift by pi over 2, subtracting a negative shift by pi over 2, and then dividing by 2. Cosine, and cosine is a different function. So this is again a little bit more general than just saying cosine is sine shifted by pi over 2, but this applies to more general sinusoids. So this is what we can call a parameter shift rule. You have a function, and that function admits a formula that says its derivative can be obtained by shifting that same function forward by some value s, some fixed value s, shifting in reverse by that same value s, and then multiplying by some constant c. This is not a general property of functions, but it's a property that some functions have, in particular functions with trigonometric structure. Very, very fortunately, it happens to be the case that quantum circuits admit a parameter shift rule. Now, the basic intuition behind this is that quantum circuits are performing interference of vectors in complex vectors in very large dimensional spaces, and complex numbers in particular have this trigonometric structure associated to them. So that means that quantum circuits inherit a lot of this trigonometric properties, including the parameter shift rule. So in general, quantum circuits, if you give it the value theta, it's able to compute sine of theta. Now, that gives us a method for evaluating this particular function. But what if we want to evaluate its derivative? Right? As I said, this function, this computing device only does one thing, evaluate that single function. The derivative of sine is cosine, and cosine is a different function from sine. However, cosine does have the interesting property that it looks like a sine, but with a phase shift. So it turns out that, I'll write it here in a bit more general form, but functions like sine or cos, their derivative can always be expressed as a forward shift by pi over 2, subtracting a negative shift by pi over 2, and then dividing by 2. So this is again a little bit more general than just saying cosine is sine shifted by pi over 2, but this applies to more general sinusoids. So this is what we can call a parameter shift rule. You have a function, and that function admits, it's sometimes interesting to consider, you can always decompose gates. And there's more recently proposed a stochastic parameter shift rule, which has the problem. For a particular gate, there is a recipe which consists of an s value and a c value, which are typically pi over 2 and infinitesimal. It's not a small number. And in fact, it's specific to each gate. So that strategy in future systems only depends on the very particular gate whose parameter you're differentiating. So when we're talking about derivatives, it's sometimes interesting to consider what happens with higher order derivatives as well. So the parameter shift method is pretty generic, and it allows you to not only compute derivatives and gradients, but higher order derivatives as well. So sometimes for optimization, it's important to take into account the curvature of your optimization landscape. So you want to compute things like the Hessian matrix, the geometric tensor, or the natural gradient, or Fisher information matrix, these kind of things. And in general, the parameter shift rule can actually be extended to arbitrary higher order derivative tensors. And you're adding more derivatives. The symmetries of quantum gates and the symmetries of quantum circuits means that you use those same estimate two expectation missing piece of the terms to compute the higher order derivatives. So this is now the missing piece. This is what allows us to apply the ideas of differentiable programming to quantum circuits. We have a tool for computing gradients. So in particular, if I have a quantum circuit and I have a single variable in it, then what I have to do is I have to estimate two expectation values. So an expectation value is kind of a bit of a hyperparameter here for you to choose how many samples you want, cases you want to average. So let's say that's 1,000, for instance. Then in order to compute the gradient of the circuit with respect to that parameter, I would have to compute 2 times 1,000, or execute the circuit 2 times 1,000 times. Now, if I want to compute the gradient, which is a vector of partial derivatives of m parameters, then I would need 2 times m times the number of shots, runs of the circuits.
The show's at 2 p.m.
The fortunate thing about this is that it can all be done automatically by software. It's all rule-based. As I said, these recipes are fixed for each gate, and so it can be done automatically by software. So this allows us to put all the pieces together. We have quantum circuits, they have free parameters, and we can automatically differentiate them by using the parameter shift rule, and then that can be a primitive to using gradient descent algorithms to train those quantum circuits. So this is really exciting. We have all the pieces we need in order to train quantum circuits. And what I'd like to talk to you about next is that it can all be done automatically by software. It's all rule-based. As I said, these recipes are fixed for each gate, and so it can be done automatically by software. So this allows us to put all the pieces together. We have quantum circuits, they have free parameters, and we can automatically differentiate them by using the parameter shift rule, and then that can be a primitive to using gradient descent algorithms to train those quantum circuits. So this is really exciting. We have all the pieces we need in order to train quantum circuits. And what I'd like to talk to you about next is actually how to use all these tools to build algorithms, to discover algorithms, or to tune quantum circuits towards particular purposes.
You remember the very simple neural net that I showed you had multiple weights. So
know what it is to be differentiable at a point, you must be defining a little area around it, a little open around it, or here a little interval. So we ask that the domain itself of the function is open, and then to be differentiable means that every point to be differentiable in the usual sense. The analog for discrete values, things like conditionals, is that the places where the condition evaluates to true and the places where it evaluates to false not only should be disjoint, of course, but they should be separately open. Okay. So the proposition is that as long as those two things are true, then the usual rule is correct. Okay. And this actually is in the literature, some version of my differentiation literature. Here's a quick proof. So suppose b of x is true. Well, then actually it's also true in a little open area around that. So in that whole open area, h and f are the same, so therefore they have the same derivatives. So now it's easy. That's good. Let's happily carry on to while loops. What's the rule there? Well, suppose h is while b do f. Suppose it goes around the loop n times, then h of that particular x is f of n to x. So therefore, derivative of h that you get by taking the derivative of f to n using the chain rule. That's false. But it's true, assuming all these continuities happen. And it's a similar argument that it's an open set. So a little bit more complicated, but it's basically that's what's going on. Anyway, how do you compute the derivative? Well, what it looks like you have to do is you have to go around the loop to find out when you're going to get to stop. So you should remember all the intermediate values. Once you've got that, you can do the chain rule backwards using the intermediate values. And you can either keep that, if it's like an interpreter or compiler, you can keep that in some separate data structure, or you can do a program transformation, which you take the loop and you translate it into two loops. The first loop goes around the first.
Hi there. My name is David Gronke. It's 12:50. We're gonna get started. Thank you so much for being here, for joining me for this talk. This is a pretty amazing opportunity, so I'm very grateful. I also want to say thanks to the Strange Loop and the organizers, and to Papers We Love Seattle for letting me present a version of this last week. Street is called a functional program into a version that only uses a very reduced set of core functions, a set of primitive functions that it uses and combines and composes to like this is a abstract virtual machine, and it's worth thinking about how we normally think of virtual machines. There's this log of a for running anywhere for a machine, the simplest graph you can imagine in memory. And what it shares with our high-level languages like Haskell or conceptually with the lambda calculus. One, maybe the idealistic option is custom hardware. We respond to this problem of not having CPUs that work for us by building our own CPUs. This has met limited success in industry. There's no shortage of master's and PhD theses about creating FPGAs to run your functional programs, but they've yet to break out of that world. But it's really interesting to look at. There was a processor that was, I think, actually fabricated in some numbers in the 80s called Norma. There's also a paper from 2008 about a chip architecture called the Reduceron. This was developed between 2008 and 2010, which I find extremely heartening that someone is working on this in 2008, about 20 years after the heyday. And it does make me wonder what would happen, if graph reduction had its heyday later in the history of functional programming, in an era where FPGAs are cheaper, where chip architectures are more sophisticated, where memory caching is much more sophisticated. But the Reduceron and Norma both tackle this. The fundamental problem with graph reduction, as described by the authors of the Reduceron paper, is that it's really memory hungry. Specifically, it requires moving tons of memory back and forth because we're shuffling this giant graph, right? This giant arbitrarily large blob in general memory. And the subtitle is widening the von Neumann bottleneck, which refers to that bandwidth constraint. And they do that with an FPGA that can, when the reductions are performed, can reach into multiple subgraphs at once and perform 8, if I remember correctly, 8 reduction steps at once, each accessing a different bank of memory. It's a cool paper. It's pretty approachable. I'll talk about links to these papers at the end. The other response to graph reduction that was more successful was what's called closure reduction. Closure reduction is a cousin to graph reduction, which could have its own talk or 5. And it's what's used by GHC. That's probably the important thing. And it's a technique for mapping call by need semantics, the semantics of our functional programming languages, to the call by value world that we live in. If you're familiar with the GHC internals, you might know that it uses C and C functions as an intermediary representation of Haskell functions. C is maybe the preeminent call by value language in our world. When we think about canonical execution of call by value programs, you're probably thinking about the C stack. And it pretty successfully maps to that world. It does that at the cost of greater complexity. The model of a Haskell function is much more complicated than the SK and I combinators. There are special cases. There's more logic, but it runs fast. It's successful, and it's proved to be a really successful compromise. I do wonder, like I said earlier, with today's chips, with today's FPGAs, if Haskell did not, and GHC particularly did not already have a dominant position, what graph reduction would look like. So if anyone is inspired here who loves FPGAs, you should work on something. See how it goes, and tell me about it. Again, thank you. I hope this is interesting. I hope this inspires people to look at this sort of weird way of executing programs. That's my fundamental interest, is that it's really a weird way of running programs. Yeah, thank you. GP was that so look at my any other questions?
Your life is going to change now. I've been waiting for you. This is your lucky day.
Words don't mean very much to you, don't worry. It should be hopefully fairly self-evident what's actually going on. But if you're into functional programming and Lisp and things like that, you might find that interesting. So just a quick demonstration. You can see this line
A certain enchanted forest is inhabited by talking birds. Given any birds A and B, if you call out the name of B to A, then A will respond by calling out the name of some bird in the forest. We will call this A's response to B, or AB. Generally, A's response to B is not necessarily B's response to A, or we can say AB doesn't need to be BA. Given the birds A, B, and C, if you call out the name of C to bird AB, you get AB's response to C. And if you call out the name of the bird BC to A, you get A's response to BC. The bird M is called the mockingbird because for any bird X, the mockingbird calls out the response of that bird when it hears its own name. So if B hears B, it will respond with BB. And if M hears B, it will also respond with BB. If A hears A, it responds AA. If M hears A, it responds AA as well. Given three birds, A, B, and C, not necessarily distinct, they might be the same birds essentially. The bird C composes if C's response to any bird is the same as A, open parentheses, BX, close parentheses, or A's response to B's response to X. For instance, if a bird G is called to B, B responds with BG, and when A hears this response, A responds with A's response to BG, and when C hears G, it also responds with A's response to BG. With this grammar and axioms, you can tackle the puzzles in Raymond Smullyan's To Mock a Mockingbird.
This is a computer program written in Python. The function Fibonacci n produces the nth number in the Fibonacci sequence 1, 1, 2, 3, 5, 8, and so on. In the Fibonacci sequence, the first two terms are 1 and 1. Some people start with 0 and 1. And each of the other terms is the sum of the previous two terms. What if I told you that this program, or indeed any computer program, can be written using just two functions? In this video, we talk about combinatory logic. Combinatory logic by getting rid of variables altogether. In combinatory logic, we have combinators that have certain behaviors. In this video, we talk about combinatory logic. In 1920, Moses Schonfinkel invented combinatory logic. Combinatory logic solves the problem of keeping track of variables in a language.
Last year, we shared with you the story of Dawood, who lost his daughter to crocodiles in tunnels.
By getting rid of variables altogether. In combinatory logic, we have combinators that have certain behaviors. Perhaps the simplest combinator of all is I, which does nothing. I is the identity combinator. Here, X can be anything, including other combinators. For example, if we have the expression I, this reduces to I by the behavior of the I combinator. The combinator K does this. For example, what happens if we have KIXY? By the definition of K, KIX reduces to I, so KIXY reduces to IY. Then, by the definition of IY reduces to Y. So whatever X and Y are, KIXY ignores X and outputs Y. Note that K takes two objects and returns the first one, while Ki takes two objects and returns the second one. The combinators K and I have combined, hence the word combinator, to produce a different behavior. We did not need to create a new combinator from scratch that takes two objects and returns the second one. Rather, we programmed this behavior by combining the two combinators K and I. We have written our first program using combinators. We can give this program a name. Let us call it the N combinator. This is how combinatory logic avoids variables altogether. Our program is simply a string of combinators. Let us try to use this program to reduce something. We first replace n with ki, because that is how n is defined. We then execute the behavior of k, reducing ki kk to ik. We then execute the behavior of I, reducing ik to k. Hence, nkk reduces to k. Notice that we are executing the first combinator in every step, ignoring the others. This is called lazy evaluation. We shall be using lazy evaluation throughout this video. The fact that nkk reduces to the combinator k means that nkk and k have the same behavior. They both take two objects as input and return the first one. We say that nkk and k are extensionally equal. Here we are not defining a new combinator. We are saying that nkk and k have the same behavior. In computing jargon, they are different computer programs that do the same thing. These three combinators all take three objects as input, f, g, and x. Let us focus on b first. B first applies g to x, then applies f to the output of gx. Thus, b performs a composition of functions. Note that the expression gx means the output of applying function g to x. In mathematics, we would write this as g of x instead, and the output of b would be written as f of g of x. Focusing now on c, c applies f to x, then applies the output of fx to g. Thus, applying f to x results in a function which is then applied to g. This is called currying, and allows us to consider all functions to have only one input. Moving on to s, s applies f to x and g to x, then applies the result of fx to the result of gx. In a sense, its behavior is that of b and c simultaneously. Thanks to currying, we can switch from fgx to fgx and back at will. Let's give some examples. The combinator ci here expects two inputs and applies the second input to the first one. In this example, SBI expects two inputs and applies the first input twice to the second input. Here, SKK expects only one input and returns it, doing nothing. So SKK is extensionally equal to I. SKSK expects three inputs and applies the first input to the application of the second input, to the third input. Thus, SKSK is extensionally equal to B. This expression has the same behavior as C, and is thus extensionally equal to it. Note that in this example, we reduced KKFGX to G only after realizing that there is no combinator in front of the expression. This is what we mean by lazy evaluation. We postpone the evaluation of expressions in inner brackets until there are no outer expressions that can be worked out. These examples have demonstrated that the combinators I, B, and C are extensionally equal to combinators involving only S and K. The B's in the expression for the C combinator can each be replaced by S, KS, K. This is very important because we are going to show soon that the combinators S, K, I, B, and C can be used to simulate any program behavior we want. In other words, every program can be written in terms of these 5 combinators. But since 3 of these 5 combinators are extensionally equal to expressions involving the other 2, any program would then be possible to be written in terms of only 2 combinators, S and K. Here's how we can write any behavior in terms of S, K, I, B, and C. We can treat this as a compiler that compiles any behavior into S, K, I, B, C expressions. Here are a few examples. Here, in fact, we get that n equals ki, as we got before. We have already seen this function before as well. M is the function that applies its input to itself. Note that since we have earlier compiled T to CI, we may say that V is BCT. This is the way we are writing programs without any variables. This is combinatory logic as Schoenfinkel intended. Here we verify that our program indeed works. So far, the only programs that we cannot turn into combinatory logic are those that refer to themselves, like this one. This is akin to a function referring to itself, where recursion would occur. For example, this is how yi would reduce if y were an acceptable combinator. It would go on to an infinite loop. We call y a fixed point combinator because yf outputs a fixed point for function f. Since yf reduces to f of yf is the value x that reduces to fx. Thus, yf is the fixed point of f, the value x reducing to fx. Loops are very important in programming languages, so we seek a combinator expression for y. It turns out that there are many such possible programs that have the behavior of y. In fact, we can prove straight away that if y is a fixed point combinator, then so is SIY. Since yf also reduces to f of yf, SIY and y are extensionally equal. There are two commonly used combinator expressions for y. One was discovered by Haskell Curry, and the other one was discovered by Alan Turing. Let us check that both fixed point combinators do as intended. Since yf reduces to m of CBMF, which in turn reduces to f of m of CBMF, we see that yf reduces to f of yf. Similarly, theta f can be shown to reduce to f of theta f. Either of these two combinators may be used to simulate the intended behavior of y. Let us use the y combinator to obtain a combinator expression for the following example function that refers to itself. We first create a new function, fun', that is just like fun, but with an extra input. Let's call it f. And with every instance of the fun function on the right-hand side replaced by this new input. We then find a combinator expression for fun'. This can be done now because fun' does not refer to itself anymore. Then function fun is just y fun'. Let us see this in action. So far, the claim that any program can be written using combinatory logic using only the combinators S, K, I, B, and C is perhaps scarcely believable. We are now going to simulate truth values, numbers, and the data structure using combinatory logic, which will hopefully make our claim more credible. Remember that we still need to implement our Fibonacci program using combinators, and we seem to be very far from that goal. Let us start from true and false. These are called Boolean values. In fact, these are the only Boolean values. Their behavior is easy to describe. The idea is that if we have a function that evaluates to the Boolean value true, then function f is evaluated, while if it evaluates to false, then function g is evaluated. We are thus simulating an if-then statement, branching to one part of the program, function f, if an expression is true, and to another part of the program, function g, if it is false. We have already converted these behaviors to combinators. Let us play a bit with these Boolean values by defining the logical connective not. We want the behavior of not to follow its usual truth table. The behavior of not would thus be the following. By our definitions of true and false, true, false, true reduces to false, and false, false, true reduces to true, which is exactly what the behavior of not should be. See, we are branching to a different evaluation depending on the Boolean value of p. Compiling this, we obtain this. One advantage of programming languages that may be based on combinatory logic, like functional programming languages, is the fact that we can mathematically prove things about our programs. For example, we can prove that not of not p is p, whenever p is either true or false. Remember, this means that p and not of not p are extensionally equal. p may be replaced by not of not p or vice versa, without affecting the behavior of the program. Here's the proof. We cannot continue the evaluation of the program until we know the value of p. We consider both possible values of p. If p is true, then the evaluation would continue like this. If p is false, then the evaluation would be thus, if p is true, then not of not p reduces to true, and if p is false, then not of not p reduces to false. This proves that not of not p and p are extensionally equal. We now simulate ordered pairs using combinatory logic. An ordered pair is usually written like this: x, y. Let us suppose our pair x, y is pair xy. We would surely want to access each of the two objects in the pair, like so. Note the similarity with perhaps we can define pair such that this happens. In other words, we would like to have this behavior. Then first p would reduce to p true, and second p would reduce to p false. We had already compiled pair previously, and first and second compile to these two. For example, first of pair xy correctly outputs x. We can also, perhaps surprisingly, simulate natural numbers. Assuming we have a representation of 0, we may define 1 as the pair false, 0, 2 as the pair false, 1, and so on. In this way, all non-zero numbers are pairs whose first entry is false. The function 0 should return true if n is 0, and should return false otherwise. So we may define 0n reduces to first n. Of course, we want 0 of 0 to evaluate to true. If we define 0 as I, 0 of 0 would reduce to I of true, which reduces to true. That's exactly what we want. So our definition of 0 works. Obviously, this compiles to 0 is defined as first. All of this happens as long as the numbers are defined in the way we have talked about. That is, 0 is I, 1 is pair false 0, 2 is pair false 1, 3 is pair false 2, and so on. We can shorten these infinitely many positive numbers into one function next. Next of n is pair false n, which clearly compiles to next is pair false. In this way, 1 would be next of 0, 2 would be next of 0, and so on. These are our natural numbers then.
No one told Jason that adulting requires you to stretch time, but you can up your adulting game with Sonnet Home and Auto Insurance. Plus, Canadian university and college grads get big discounts.
Kids, look, I'm doing it.
Which represent 0, 1, 2, 3, and so on. If n is a positive number, then we can prove that it is extensionally equal to pair false n minus 1. So the number before n is easily accessible. It is the second entry of the pair. We are getting closer and closer to the Fibonacci program. But first, we need to simulate the behavior of applying a function n times to some input x. In other words, we want something like this. For example, adding two numbers m and n is the same as applying next m times to n, that is, and this compiles to. We still need to define the function apply though. We can read this as if n is 0, then output x, else output f of the output of apply n minus 1 fx. Since this function refers to itself, its conversion to combinatory logic will involve the y combinator. Brace yourselves. It's a very complicated behavior, so it's a very complicated expression with combinators. But now we have everything in place to write our Fibonacci program. Recall that we want to write a program that outputs the nth number in the Fibonacci sequence 1, 1, 2, 3, 5, 8, and so on. We keep track of our sequence using pairs. Let us first write a function that, given any two consecutive terms of the Fibonacci sequence, outputs the next two consecutive terms of the same sequence. For example, if we give it the pair 1, 2, it outputs 2, 3. Or if we give it the pair 5, 8, it outputs 8, 13. The output is the pair where the first number is the second number in the input pair, and the second number is the sum of the two numbers in the input pair. The function that does this would be the following, which we can compile straight away. Now, all we need to do is to apply next pair n times to the pair 0, 1. Then read off the first number in the resulting pair. For example, if we apply next pair to the pair 0, 1 once, we obtain 1, 1, and the first number of this pair is the first number in the Fibonacci sequence. If we apply next pair to the pair 0, 1 twice, we obtain 1, 2, and the first number of this pair is the second number in the Fibonacci sequence, and so on. So we have this expression. Note that the number 1 is represented as next 0. And this behavior compiles to this expression. So that is it. Each of the functions first apply next pair, pair, and next have a very specific definition in terms of the combinators s, k, i, b, and c, and other functions or combinators like t and n. But these other functions and combinators are also ultimately defined in terms of the combinators s, k, i, b, and c. So at the end of the day, fib is defined in terms of the combinators s, k, i, b, and c. But that's not all. Since the combinators i, b, and c may each be written in terms of s and k only, the program fib may be written in terms of the s and k combinators only. If you are still watching, then we have a bonus bit especially for you. We have just concluded the previous part by reminding you that we are always able to write any program using the two combinators s and k. But is there one universal combinator with which we can write any program? It turns out that there is. It is called the iota combinator and was discovered by Chris Barker in 2001. With this definition, iota is extensionally equal to I. Iota of iota I is extensionally equal to k. And iota k is extensionally equal to s. Thus, the iota combinator alone is enough to write any computer program. Every combinator expression involving s, k, and I can be transformed into one involving only the iota combinator by performing these replacements. This is one of the most astonishing results in mathematics and computer science. Here's how our Fibonacci program would look like if we used only iota. This video is our submission to the second Summer of Math exposition. We, Alexander Farrugia and Giorgio Grigolo, wanted to explain the basics of combinatory logic to the world for a very long time. This year's Summer of Math exposition was the perfect medium to do so. Thank you for watching this video. It really means the world to us.
Eric Hainer is a Canadian computer scientist who developed an interesting unified approach to logic and arithmetic. It's quite remarkable. He introduces many cool ideas, some of them perhaps far-fetched, but what I like most about them is that they make you think, and they give you new insights. They are the perfect example of what we are trying to do on this channel, looking at familiar things from a new angle. Some time ago I asked you if you would be interested in a video about Hainer's new system, and many of you responded positively. So here we go. Logic begins with two opposite values that are often called true and false, but you can also think of them as on and off, or high and low, or good and bad, or any other pair of values that are opposites of each other. Hainer calls them top and bottom, and gives them these two symbols. The names top and bottom come from a theory about partially ordered sets, where the top element is larger than all others, and the bottom element is smaller than all others. Hainer is very sensitive to the visual shape of mathematical symbols. When symbols are carefully chosen, they sharpen your intuition and make your calculations easier. So it's no coincidence that the top and bottom symbols are each other's vertical duals. This choice reflects the fact that they are also mathematically opposite to each other. The two binary values can be combined using various operators. The first one is typically called AND, because its value is true only when both of its inputs are true. But Hainer looks at this differently. He urges us to think of top and bottom as two values that are ordered. Top is the largest of all possible values, and bottom the smallest. This allows us to interpret the AND operation as the minimum instead. Its value is top only when both inputs are top. As soon as one of the inputs is bottom, it pulls the minimum down, and then the other input value becomes irrelevant. Another classical operation is called OR. Its value is true when one input or the other is true, or possibly both. In our new interpretation, this is the maximum of the two input values. As soon as one of them is top, it pulls up the maximum and the result is also top. The classical symbols for AND and OR are these wedges, pointing in opposite directions. Again, this is a perfect choice because the operations are dual to each other. But they are also perfect in another respect. They are symmetric around a vertical axis. This helps you remember that these operations are commutative. X and Y has the same value as Y and X. The maximum of A and B is the same as the maximum of B and A, and so on. Hainer carefully chooses his symbols so that they reflect these algebraic properties. He sometimes uses these arrows instead of the wedges, because they spell minimum and maximum more clearly. And they are still vertically symmetric and horizontally dual. Here's another key operation on binary values. It's called implication, and it says that if the first input is true, then the second must be true as well. If the first input is false, the second input can be whatever you want. This is one of those things in logic that confuses the hell out of students. How on earth can something false imply something true? It would be like saying, if 2 plus 2 equals 5, then I am the Emperor of China. Logically, this is absolutely true. Intuitively, it makes no sense. But if you look at it from an ordering perspective, it all becomes clear. Think of implication as less than or equal to. Because bottom is less than top, this rule now makes perfect sense. So this idea of using order theory as a model for binary logic isn't as weird as it may seem at first. It's actually very insightful. Think about numbers and proofs for a moment. If x is less than 4, then it's also less than 6. The first condition implies the second, and this is how you would typically use implication in mathematical proofs. But now look at it like this. The condition that x is less than 4 is stricter than the condition that x is less than 6. Fewer values for x satisfy it. And so you could say that the first condition is less true than the second one. Mathematical statements are ordered from bottom to top, from the falsest statements that aren't satisfied by anything, to the truest ones that are satisfied by everything. So even the notion of mathematical proofs can be reformulated in terms of ordering. Even though top and bottom are dual to each other, mathematicians have a preference for top. When a logic expression evaluates to top or true, we say that it's a theorem, and we award it special status among all other mathematical statements. Some statements are always true. They evaluate to top no matter what values you fill in for the variables. Those statements are called laws. A good example is the law of the excluded middle. No matter what value you give to the binary variable q, the value of q or not q is always true. You can easily prove this yourself by just looking at the truth tables. The next thing we're going to do is extend binary logic to arithmetic. In computer science, you will often see the number 0 used for false and 1 for true. Hainer's solution is much more surprising, until you remember that it's based on ordering. Top is larger than all possible values, including numeric values, so it makes a lot of sense to model it as plus infinity. Likewise, bottom becomes minus infinity. This way, binary logic is embedded inside the number system in a very natural way. This turns out to be a genius move, because it gives us countless cool connections between logic and numbers. Here's one of my favorite examples. Start with two positive numbers a and b. Take their maximum. Then change its sign so that it flips over to the other side of the number line. So we have the inverse of the maximum. Now flip the original two numbers so that they both become negative. Take the minimum. I'm sure it's no surprise that this gives us the same result as before. We can write this down as a law. The inverse of the maximum is always going to be the minimum of the inverses. I don't know how familiar you are with binary logic. You may have seen this law before. Let me replace Hainer's minimum and maximum symbols with the more traditional wedge symbols. Does this ring any bells? It's the well-known law of De Morgan. Is it currently raining and snowing? If not, then it must be either not raining or not snowing, or possibly neither. The cool thing is that the same law now works for binary truth values and for numbers. I think that's absolutely brilliant. There are many more examples, such as the inverse of the inverse is the original. See if you can put these other laws into words, both for binary logic and for numeric values of x. You can share your interpretation in the comments, so that we can discuss how these connections between logic and arithmetic can be understood. Now, we have to be careful, because there are laws from binary logic that don't carry over to arithmetic. One important example is the law of the excluded middle. When q can only be a binary value, q or not q is always true. But when q is a number, This formula asks us to calculate the maximum of q and negative q. The result is the absolute value of q, which is definitely not equal to true or top or plus infinity. So the law of the excluded middle is no longer a law in our extended system. This is okay. It's actually very common. Whenever you extend a system with new elements and new possibilities, you sometimes also lose things. We saw this before when extending the reals to the complex numbers, the quaternions and the octonions. We lost things like commutativity and even associativity. You can't always get things for free. A function maps elements from one set to another in a certain way. When you define a new function, you place the input variable between parentheses, and then you use that variable inside the expression on the right. You can use any name you want for this input variable. It exists only inside the function. You can't use it on the outside. Heiner's notation makes this more explicit by enclosing the function definition in angle brackets. The variable exists only inside the brackets. In computer science, this is called a scope. Variables exist only inside their scope. They are local to their scope. You may think that this new notation is overkill, but note that it contains more information than the original definition. It tells you the domain of the input variable. It tells you that x is a natural number, not something else. The biggest advantage of the new notation is that it also works for many other mathematical symbols that introduce new local variables. Think about the sigma notation for sums. This example introduces a new variable I that takes on all the values from 1 to 10 and then sums up the squares of those values. Heiner simply puts a plus operator in front of the angle brackets. You could even make the plus symbol slightly bigger to stress that it operates on lots of values in sequence. The advantage is that you don't have to invent a new symbol, such as the sigma. You can just use any existing binary operator. Here's how you would write a product. Just use the binary multiplication symbol. We still specify the range of input values, but now we do so consistently inside the brackets, where the scope of the variable is clearly delineated. You can also take the minimum or the maximum over a collection of numeric values. If the output expression of the function is binary, true or false, the minimum and maximum become the logical and or operators. And if you think about this a little longer, you might realize that this plays the role of the traditional for all and exists operators. For all x means that you're going to evaluate the output expression for each value of x, and then check whether all of those output values are true. This means that you implicitly put a binary AND operator between all of those output values. The new notation makes this more visible, by placing a big AND operator right at the start. So once again, we didn't have to invent a new symbol like the upside-down letter A. I remember being charmed when I saw this for the first time. There really is no difference between the minimum, the logical AND, and the for-all quantifier. They all do the same thing, so they should all be written with the same symbol. This makes it much easier to understand what the exists quantifier does. It just puts an implicit OR between all the expressions. As soon as one of them is true, the entire thing becomes true. Let's look at that simple function definition again. The original has a name. It's called f. The new definition doesn't have a name. It's just a thing that maps inputs to outputs. If you want to give it a name, you can. Just assign the thing to a brand new variable, like you always do. And since, by definition, the bracket expression on the right is now the same thing as the letter f on the left, we can now write a big sum like this. You no longer see the range of input variables because it's carried around inside the letter f, if you will. This allows for some very compact notation. Here are the laws of De Morgan again. Look at how brief they are. Heiner even suggests that we could drop the f entirely, which reveals that De Morgan basically says that AND is the opposite of OR. Personally, I would say that this is pushing the limits of readability. You don't want your notation to become so compact that you forget what it means. But for lengthy calculations, this might be a huge time saver. A set is a bunch of elements that you put together inside a box. The set itself is the box, and the elements of the set are the contents of the box. Traditionally, you write a set of elements like this. You can think of the curly braces as the box. But Heiner goes one step further, and once again this is a really curious and fruitful way of looking at things. These commas are not just punctuation signs that separate the elements from each other. The comma is a binary operator. It takes two inputs, let's say the numbers 2 and 3. It combines them into a bunch. A bunch is just a collection of objects that are not yet placed inside a container. The curly braces are a unary operator that turns a bunch into a set. It puts the bunch of elements into a box. The empty set is just a box with no elements inside. An empty bunch is literally nothing, not even a box. Seeing the comma and the braces as operators rather than mere punctuation marks is extremely clever. You probably know that the order of the elements in a set is irrelevant. For Heiner, this can only mean one thing. The comma operator is commutative. It's so elegant to reuse the concept of commutativity here in a totally different context. And it gets even better. The comma operator is also idempotent. This simply means that if you add the same element into a bunch or set twice, you get only a single copy of it. This is similar to how projections are idempotent because projecting twice is the same as projecting only once. So we turn the comma into a full-blown operator with properties that it shares with many other operators. This efficiency of concepts is very typical of Heiner's system, and it's the main reason I like it so much. In set theory, you can specify that something is inside a set by using the element of operator. Heiner prefers to write this with a colon. This expression says that n is a natural number. One important difference is only a single copy of it. An empty bunch is. You can think of the curly braces as the box. But Heiner goes one step further, and once again this is a really curious and fruitful way of looking at things. These commas are not just punctuation signs that separate the elements from each other. The comma is a binary operator. It takes two inputs, let's say the numbers 2 and 3. It combines them into a bunch. A bunch is just a collection of objects that are not yet placed inside a container. The curly braces are a unary operator that turns a bunch into a set. It puts the bunch of elements into a box. The empty set is just a box with no elements inside. An empty bunch is literally nothing, not even a box. Seeing the comma and the braces as operators rather than mere punctuation marks is extremely clever. You probably know that the order of the elements in a set is irrelevant. For Heiner, this can only mean one thing. The comma operator is commutative. It's so elegant to reuse the concept of commutativity here in a totally different context. And it gets even better. The comma operator is also idempotent. This simply means that if you add the same element into a bunch or set twice, you get only a single copy of it. This is similar to how projections are idempotent because projecting twice is the same as projecting only once. So we turn the comma into a full-blown operator with properties that it shares with many other operators. This efficiency of concepts is very typical of Heiner's system, and it's the main reason I like it so much. In set theory, you can specify that something is inside a set by using the element of operator. Heiner prefers to write this with a colon. This expression says that n is a natural number. One important difference is that NUT is the bunch of all natural numbers, it's not a set. We should use bunches rather than sets, especially when specifying the domain for a variable. That's because there's one final trick we can pull. You've heard about distributivity, right? Multiplication distributes over addition, so you end up repeating the factor of 2 for each of the terms. Well then, since the comma is now a binary operator, it can participate in distributivity. All other operators distribute over the comma operator. So when you say NUT plus 7, you get the bunch of all natural numbers that are at least 7. And 2 times int is the bunch of even integers. NUT squared gives you all the square numbers, and so on. The reason this works so well is because we are operating directly on bunches, so we don't have to unpack and repack anything, which makes the formulas extremely elegant. It's now easy to construct new bunches from other bunches, and once again, you just keep using the same old operators that we already had. This is especially powerful in computer science, where you have to be very precise about the domain of each variable. You can now easily start playing around with these ideas yourself. If the curly braces turn a bunch into a set, there could also be an inverse operator that turns the set back into a bunch. It takes the elements out of the set and throws away the box. Let us know in the comments what other kinds of clever tricks you can come up with. There are a few links in the description to Heiner's PDFs that you can download if you like this kind of out-of-the-box thinking. Don't forget to subscribe and like the video. And if you want more content like this, consider supporting us on Patreon. Our channel needs your financial support, so thank you.
In the last episode of this series, pun intended, we hinted at the use of the geometric series in understanding the Taylor series and generating functions. But what are those two ideas? Well, they're both essentially
I've got to go. I gotta go. I gotta go. Go, 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 go. Got to go. Got to go. Got to go. Donate. G-Gens. G. Wow, wow, wow. I'm just trying to hook up something here so I can do remote. Looks like my meeting's canceled. Yeah, okay, so unfortunately my meeting's canceled again. So that means Thursday instead because there was a sewer backup. Great. So I guess I'll just get back to work. I'm going to take a break for a little bit and then so I'll keep the stream going. I'm going to take a break for about 15 minutes since my meeting has been canceled, and I'll get back to what I was doing. Okay? Okay. Let's just get the tell you what, I'll play another one of those videos on the logic thing again. I think I need to review that again because that looked really good. Let's clean it up in here. So my hair's a mess now. Anyway, whatever. Gives a crap. Your studio.
Too much time has passed, and I have reached the last point of my points. The end has come. This is the final act, in which my rules defined a servant to all who find myself to be lonely compared to them. This is the final act. This is the end. This is the final act. This is the end. Balls give me tight, try to struggle, cannot fight. I wanna leave my legs to the side. No freedom till the day I die. No freedom till the day I die. Then they realize my life was not paralyzed. I had my share of work, but now it's through, no more to do. This is the final act, the end has come. This is the final act, the end has come. I'm balls grip me tight, but I've broken them tonight. I can breathe again, I had to leave. My legs were tied, I had to leave. My legs were tied. cocaine and I shot my woman down. Went right home and I went to bed. I stuck that 1144 beneath my head. Got up this morning and I grabbed that gun. I took a shot of cocaine and away I run. Made a good run, but I run too slow. They overtook me down in Juarez, Mexico. Laid in the hot joint, taking the pill. In walked the sheriff from Jericho Hill. He said, Willie Lee, your name is not your town. You're the dirty hack that shot your woman down. Oh yes, my name is Willie. If you got a warrant, read it to me. Shot her down because she made me sore. It was her daddy. I thought it was her daddy, but she had 5 more. When I was arrested, I was dressed in black. They put me on a train and they took me back. Had no friends would go my bail. They slapped my dried up carcass in the county jail. The next morning, about 9:30, I spied the sheriff coming down the line. Up then he coughed as he cleared his nose. He said, well, come on, you dirty hack, and to that district court. To the courtroom where my trial began, where I was held by 12 honest men. Just before the jury started out, I saw that little judge come as to look about. In his 5 minutes, he walked a man, holding the verdict in his right hand. The verdict read in the first degree. I hollered, Lordy, Lordy, have mercy on me. Judge, he smiled as he picked up his pen. 99 years in the Folsom pen. 99 years underneath that ground. I can't forget the day I shot my woman down. Come on, all you gotta listen to me. Lay off that whiskey and let that cocaine be. from it all. Just turn your back. You'll never hide away from it all. You'll always put your face to the wall, afraid to fall. If you're standing tall, you never had your back to the wall. You had it easy. What do you lie?
let's get back to the questions. Yes, they're trying to cancel Vlad Kostia because he's Roger, and short of it, and that's the best we can do. Basically, he's the big bad guy for talking to blockers, not allowed in BTC cancel culture, but it is what it is. Let's turn my camera resolution even lower of everyone's sanity. Yes. Low definition. Low def Kurt. There we go. Okay, cool. Next question, please, Mr. Ward. Where do you see AI and blockchain overlapping? So there's a huge overlap in AI and blockchain, and here's AI requires data. It all AI does is ingest lots of data and then try to make sense of it. Now, the best way to fool AI or make AI malicious or make it unhealthy in some way is to give it bad data. Now, if you give it bad data, it's going to consistently give you back bad everything. So the power of blockchain is in data provenance. It's in distilling the quality of data. Proof of work solves the Byzantine generals problem, but what the Byzantine generals problem really is it's about tuning out bad information and only tuning in good information. And if you can do that using proof of work and blockchain, etc., well, now that data can become very useful to the AI, which the AI right now, I'm sure they're using lots of proprietary algorithms in order to basically do what they do. But the problem is that if you've just even used ChatGPT, sometimes ChatGPT lies to you in a very convincing way. And so blockchain can basically distill data down to only its most useful variant. And that itself would be extremely valuable going forward. So next question, please. Also, I think I may have to hurry with my questions here because missed about 10 minutes of time there. Any follow-up about the BSV Hackathon winner related to video? Paying per second. Actually, I'm not sure. Shoot, what was that project even called? So there was Bitcoin Phone that had audio, basically using unlock time and some other stuff over Bitcoin. I don't know. So those hackathon winners, well, there's a few hackathon winners that are still doing all kinds of cool stuff. Like Luke Rowanaz, for example, was the Tonic Pow. I think he was the runner-up. The other one from that era was BitPing, like Dean Little and his team. There was a couple others. I don't know. I don't remember the pay per second video or where they're at. So sorry. Next one, please. How much Moon versus Wooker Jr. PowerPoint. So we are going to have to figure that out. I'll tell the story for those who are unaware. We were in Las Vegas in, gosh, it's got to be 20. It was the Consumer Electronics Show, CES, in Las Vegas. Now, me and Mr. Moon were manning the big BSV, like super booth, for a good chunk of the time, but we decided to go take a walk, and we were in like the looking for automotive. So there was like an automotive technology area, and then there was one of those measure your punch machines. So I've been, involved in martial arts my whole life. I was an MMA coach and all this other stuff. And I'm not admittedly a striker. I've never said I was like a particularly good boxer or anything, but I'm capable. I know how to box, and I'm also quite big. I'm at the time was, I don't know, 300 pounds or something. And, I'm 6'3" and know how to punch. So I go hit the thing and I get like I don't even know, 875 pound per square inch punch, which is a really good number. And then Alex shows up and goes and punches it, and he gets like 965 or something. Just absurd. He breaks the record of the day. Now, to Alex's credit, Alex probably weighs, I don't know, 75 pounds less than me, but he's also very dense, and he's got brilliant, perfect form. He's a very good boxer. And man, he he wailed on this thing, broke the record on the machine. He ended up winning some kind of a device that for your car, like it was a giveaway thing for the show. And but it was just wild, and we have it all on film somewhere too, so we're gonna have to check that out. But anyways, he killed it, totally crushed it, and we're gonna have to have some kind of a rematch here once we get all of our ducks in a row and get that straightened out. So that's definitely a thing. Maybe we can get one of them at London Blockchain Conference and give something away there. So, all right, cool. Next one, please. Ehrlich, how much does the price of BTC have to be profitable for miners post-halvening? Asking for a friend. So it's a difficult question to answer because Bitcoin really is anti-fragile in the way that it works. So if the price dropped precipitously, and like it took a big drop today, markets are down. Today's a big red day. And ultimately, the price, when that happens, all of a sudden your ASICs, especially your least efficient ASICs, will all of a sudden to lose their ability to make a profit. So they're consuming too much electricity, or they're consuming more electricity than they can overcompensate for with the machine. So the machine might burn $50 an hour, but it can only earn $40 an hour. So that machine is the kind of machine that you would go ahead and turn off in that situation. However, when that kind of thing, you turn your machine off, Bitcoin, it understands that the machine has been turned off. And if too many machines get turned off, the difficulty will adjust down, which will then raise the profitability of each machine that is back on the network or still on the network. And so it is a little bit self-healing in that regard. Now, if it were to take a huge drop, I mean, if it were to drop to, $15,000 again inside of a week or two, like the bottom totally falls out of it, you would see, bankruptcies and stuff in a few mining companies. Not your biggest few, but certainly in the bottom half of all mining companies, you'd see a lot of them just like pack up shop because they can't pay their bills. They've got too much overhead. The bank calls the note on your debt essentially, and you're wrecked, right? So it's not a real easy question to answer. But when the halvening happens, and I think on BCH, I think it happens tomorrow, and then BSVs happens in the next few days, and then BTC happens a little bit later, in like a week from now. Now, what the halvening is every 210,000 blocks, the number of Bitcoins that you get per block, new Bitcoins that are entered into circulation, those get cut in half. And so we are about to enter the 3 1/8 era or epoch of Bitcoin. And so when that happens, if the price is not double what it was when you started making all of your calculations on your debt and all the other stuff that, whatever went into you buying a place, well, then big trouble. And you can usually get back basically because the difficulty adjusts down. Now, that's not a perfect thing because if the price just keeps trending down forever, difficulty keeps trending down forever, then all of a sudden it gets to a point where you could not mine, like you can't ever get back. Because there's only a certain amount of economy that can be supported by a certain sized economy. So, it starts to turn into a macroeconomic conversation, and it would really take the rest of the show to kind of explain the calculus problem that goes into that. But to answer your question, it really depends. If you're a company that is over leveraged, if you really need to cash in all the Bitcoins you mine every month in order to pay your electric bill and service whatever debt you have, you'd be in big trouble. Weeks after in order to try to make it up, and you can get yourself into a vicious cycle. But if you're not in a particularly bad position, honestly, you'd probably be fine if it dropped to 25 grand and sat there for months at a time, because that's just how it works. When other people dip, it's good for the people who stay. So that's that. Next question, please. La la la. Hi, Kurt. Or hey, Kurt, rather. How are you guys? Hope all is well with you, Mr. Moon. Two-part question. One, do BSV or any other chain use AWS right now to keep transactions or to process them all? Two, if yes, then why do we need a blockchain? So AWS, like Gorilla Pool doesn't use AWS, but we do use different cloud providers for different things. We also run our own bare metal in a couple of privately owned spaces, one of which is privately owned by one of our business partners. But I'm going to adjust my camera down a little bit here. So AWS they're just a cloud provider. They're the biggest cloud provider. They are Amazon Web Services, one of the biggest companies in the world. And the reason you would use the blockchain is because it's a different kind of data provenance. So you probably wouldn't want to have everything in AWS for various reasons, not the least of which is insufficient level of decentralization. Like if AWS goes down, the whole blockchain goes down. That would be a bad thing, but that's certainly not how the system works. Now, over time, and actually Amazon is a good example of this. So Amazon used to run on the internet, but now the internet runs on Amazon. And so it sort of became recursive in a way that might not have been predictable, in 2002 or something, but and so it's can be okay. And solutions to these sorts of problems are economic. Like if the economy can make a solution that the economy will pay for, then it's fine. Like it's not an issue. So yeah, I don't see a problem with using AWS fundamentally, but it would be unwise for everyone to be on, like for every node on the network to be on AWS. But if you look at BTC, you can see where BTC node IP address on AWS too. So Coinbase and some of these like commercial entities that have to have nodes for commercial levels of uptime, they're using AWS for these kind of things. So it's not like this is an exclusive BSV situation. Like basically everybody uses AWS for something. So I wouldn't worry about it. About halfway here. Separate from verifying transactions and adding them to a block. Yes, they are completely different, broken out, separated, specialized processes. So all of the stuff your node is doing about validating, which you could call that transaction processing or block validation or transaction validation, they're all essentially the same thing. So when people broadcast a transaction to the network, the transactions, they propagate over the peer-to-peer network, and then they make it hopefully to all the nodes on the network. And then all the nodes have them in what is called their mempools, which is kind of like a waiting tank for your block template. Now, every one of those nodes, if they are mining nodes anyways, they are proposing a block template. And among well-connected nodes, block templates are not transactions are propagating among us. Now, if Gorilla Pool, for example, my company, is the one that finds the valid hash, which is the only thing that proof of work is doing a guess and check on a list. It's just a list of hashes, and it is doing, is this the right one? Yes or no? Is this the right one? Yes or no? Is this the right one? And if the answer is yes, then our node proposes a block to the rest of the network. And then it becomes the accepted block when somebody builds upon that block. So, but that is just a signaling mechanism about validity. It is not validation itself. The validation is actually done inside of totally separate computers on totally separate systems, but they communicate. They're connected to each other, but they are essentially separated out into other specialized processes. So validation is happening. It could happen. Next question, please. Why is the price of BCH going up? If the halving for them is here, shouldn't it be going down because it's less profitable? People are saying it's the halving meme. So people will say, well, it's getting more more is being inflated by less, if that makes sense. So the number of coins continues to go up, but it's going up at a lesser rate. So the level of inflation is going down, not the absolute scarcity of the asset. But that meme about it is that, man, it's getting more scarce, so it's got to be more valuable. Also, I have to apologize for my connection. I think my internet line got cut, and I'm trying to do this over my 5G. Admittedly, not very good because my house is concrete. Sorry. Best I can do with what has happened here. Next question, please. Can you hear me, Brandon? If the halving is 210,000 blocks and the miners get only the block fee for rewards or mining, is BTC not obsolete with just 7 CBS compared to 1 million transactions in BSV? I think over time, yes. Now, what they will tell you, their argument is that if a transaction in BTC, like full blocks, right? So there is competition to get into block space on BTC, then the price of each of those things will end up being higher, because it's like if you only have one road between New York and Washington, D.C., but you got to get there, you should expect the tolls to be $100 per trip, right? So that's kind of what's going on in their economics, that if they keep the blocks small, the toll price will, in which case they are continue to make more money forever. Now, what I don't like about that is it's essentially a planned economy, and the assumption that people are just going to be willing to pay a bigger and bigger number to use that blockchain no matter what. And that's observably false, because BTC fell below about 50% total in like 20. It very rarely makes its way back over 50, and every time it makes its way back over 50, it trends back down again. So it's obvious that people want to use other blockchains, that, BTC is not your only choice. Now, the flip side for BSV is what we will argue is that if you have larger block space and we encourage more people to make more transactions, then you're collecting lots and lots of transaction fees that can trend up forever in total volume while keeping transaction fees low. So what we believe is that commerce should be cheap to engage in so that you encourage more commerce to occur. And when you do that, then you're profitable by total volume versus profitable by, each transaction is very expensive to do. So the analogy that I like to make is it's kind of like the steakhouse business model versus the McDonald's business model. Your steakhouse needs $100 a plate in order to be profitable, and they are profitable, but they're not really scalable. There's not that many high-end steaks in the world, and there's not that many people who are willing to pay for an expensive steak dinner. They sell billions of burgers. And so those are two very different but sort of related business models, and that's kind of the way that goes. So those are my thoughts. Next one, please, Mr. Ward. Also, can you confirm, I see my video is trash, but is my audio acceptable? Everybody, please let me know. Nelson, is it true that BTC ordinals and all chains beside BSV stores content in the witness data, so the JPEGs are not really even on chain? This is correct. So witness data is in a separate Merkle tree on BTC. So this is what SegWit did. Is it set up an entirely different Merkle tree that hashes and stores your signature data somewhere else, and then it only gives the hash back, and basically says, I have witnessed your signature, hence segregated witness, or SegWit. That's where the name comes from. Now, ordinals on BTC and the other chains, they are storing data in that witness data, which is itself prunable. It's kind of like op return in that, yeah, it's on chain, but it doesn't have to be on chain. It's not part of the core UTXO set or one of the completely permanent things in the Bitcoin space. So in theory, if everybody pruned all the witness data of all the ordinals, then it's gone. And then what you're actually trusting is that the problem is that do that over time for the service, and that's that's its own problem. On BSV, it's a little bit different. So it's actually stored in outputs of the UTXO. So they're stored in actual sats, actual Bitcoins, and they are therefore permanent in a way that BTC ordinals are not. So that's that. Next one, please. Did you see the Brian Keating YouTube podcast with Michael Saylor, Randy? No, I did not. If it's recent, anyways, I haven't seen it. Saylor's a nut. Saylor's always been kind of a party boy. So I live near Miami now, so I know a lot of people that have known or done business with Michael over the years, and he's famous for a great many things. One of them is kind of the parties a bit, and makes very strong gambles on things well on his BTC. That's great, but he's ultimately something of an irresponsible in many regards. And I can't stand his sort of the Giga Chad bombacity meme that they've made about him, because he really is just a kind of degenerate gambler type. Done well. The losing most investor living. I think he lost something like $14 billion in one day about 20 years ago. And then overall, hello again. Sorry, everybody. Next question, please, Mr. Ward. I think if I cut out again, I should quit and go talk to
quantum computer will be able to perform certain tasks significantly faster than any traditional computer, your phone, your laptop, and even the fastest supercomputer in the world. Demonstrating this is showing quantum advantage, an enormous milestone on the way to a full, fault-tolerant quantum computer. Previously, only 2 teams worldwide, one from Google and the other from USTC in China, had demonstrated quantum computational advantage. Now, here in Canada, Xanadu has joined the ranks of these monumental achievements with its own demonstration.
At Xanadu, we achieved this breakthrough using the power of light. And even better, we put our device on the cloud. So anyone in the world with an internet connection can access quantum advantage for free.
Xanadu was founded over 4 years ago with the mission to build quantum computers and to make them useful and available to people everywhere.
What makes Xanadu's approach different is that we base our computers on photonics, quantum states of light. Last year, we set ourselves the ambitious goal of demonstrating quantum advantage and making it available on the cloud for the first time.
It's extremely challenging to prove that you have demonstrated quantum advantage. For our
quantum computer will be able to perform certain tasks significantly faster than any traditional computer. Your phone, your laptop, and even the fastest supercomputer in the world.
Xanadu's approach different
that you have demonstrated quantum advantage. For our demonstration, we chose a hard mathematical problem, sampling random numbers from a special probability distribution. Simulating this with a classical computer will require the computation of a difficult mathematical function called the Hafnian.
In general, calculating a property of the Hafnian by hand or with the help of a traditional computer, no matter how powerful, can take a prohibitively long time. But it can be sped up substantially with a quantum photonic device in what's known as Gaussian boson sampling, or GBS, sending squeezed light through an interferometer and counting the photons at the output.
However, the GBS experiment with hundreds of squeezed light qubits, which was our aim, required a bit of a redesign. Instead of arranging hundreds of squeezers and beam splitters in space to generate and entangle the qubits, we made use of time multiplexing, where a single squeezer generates many pulses of squeeze light. Some of these pulses are stored in optical fibers while waiting for the next one to arrive and be entangled at just the right time. The fibers act like buffer memory. We can process 216 qubits into the right quantum state without each qubit needing its own dedicated hardware.
At the end, detectors count the number of photons in each pulse. The photon number pattern that we observe is the sample in Gaussian boson sampling, the process that is so difficult to directly simulate without a quantum computer.
To confirm that our experiment was indeed hard to directly simulate, we benchmarked our quantum device against state-of-the-art algorithms on fast classical supercomputers. After a lot of careful analysis, we concluded that our demonstration went well beyond current simulation methods, requiring hundreds of millions of years to recreate on the world's fastest supercomputer.
To make sure that our quantum advantage demonstration was more than just a one-off experiment, we're also hard at work making it available to all the users of Xanadu Cloud.
Everyone came together, from quantum theorists to engineers to developers, for the final push to make quantum advantage available on the Xanadu Cloud.
The last weeks were spent chasing bugs, connectivity, and stability issues, making sure that this device had the operational readiness that is expected of cloud-available quantum hardware. The last mile was the integration.
Imagine controlling a computer the temperature of interstellar space, connecting to the basic elements of the universe from your laptop, crunching numbers using the vibrations of particles, running computer programs directly on a cloud of atoms, solving hard problems with frickin' laser beams. Welcome to the awesome realm of quantum computing. Welcome to Penny Lane. Penny Lane is open source software for programming quantum computers. You may have heard the hype about the power of quantum computers. Some of it is even true. Right now, trailblazers worldwide are building a new technology unlike anything we've seen before. But the world of quantum computing is still wild, still untamed. Quantum computers should be useful and available to people everywhere. We're on our way, but there's much more to build, much more to discover. They say it takes a village. All of us, a global community, working together to bring quantum computing into its full potential. It's gonna be amazing. Imagine studying the most inscrutable properties of molecules by using other molecules, training a quantum computer the same way as a neural network, connecting to every quantum computer available today, or even combining them together to make something greater than the sum of its parts to unlock the full power of quantum computers. We'll need to do things no one has ever done before, things no one has even thought of doing before. It's going to take big ideas, new ideas, your ideas, teachers, students, scientists, artists, enthusiasts. Thousands of people worldwide have already joined Penny Lane's quantum computing community. Everyone has a part to play, a unique contribution to make.
Xanadu is developing photonic chips for near-term quantum computers. These X-series chips are made out of silicon and silicon nitride and consist of three primary modules: squeezers, the input to the computer, an interferometer, the logical gates, and photon detectors, the measurement output. Let's look at each in more detail. Classical laser light is first distributed to an array of squeezers. These microscopic devices are made of small ring resonators, which, when driven by bright classical laser pulses, generate a special quantum state of light called a squeezed state, Xanadu's version of a qubit. These states involve a quantum superposition of different numbers of photons, and, once generated, are coupled into an array of bus waveguides, which carry them to the next stage. The squeezed states now enter a network. These states involve generate a special quantum state of light called a squeezed state, squeezers. These microscopic devices are made of small ring resonators, which, when driven by bright classical laser pulses, generate a special quantum state of light called a squeezed state, Xanadu's version of a qubit. These states involve a quantum superposition of different numbers of photons, and, once generated, are coupled into an array of bus waveguides, which carry them to the next stage. The squeezed states now enter a network of beam splitters and phase shifters called an interferometer. To program the interferometer, the user's instructions are loaded into the chip electronically. The control system translates these instructions into a set of electrical voltages that are applied, which carry them to the next stage. The squeezed states now enter a The control system translates these instructions into a set of electrical voltages that are applied to the different components on the chip, loaded into the chip electronically. The control system translates these instructions into a set of electrical voltages that are applied to the different components on the chip. The squeeze states interact with one another and are entangled, a prerequisite for quantum computing. The interferometer can be thought of as a sequence of quantum gates acting on the inputs. In general, the output of the interferometer is a highly entangled quantum state encoding the processed quantum information. The quantum state is now ready for readout. Each output of the chip is directed to a special photon detector called a transition edge sensor. These detectors count how many photons are present in each output, yielding an array of integers that are reported back to the user. The results of the computation or algorithm are encoded in the statistics of this photon number data. The Xanadu X-series chips are useful for solving complex problems in the domain of graph theory that are relevant for finance, chemistry, and logistics. And it's all available on the Xanadu Quantum Cloud.
Isn't that cool? Oh. Isn't this the coolest thing? Well, just about. Go turn it off. Now, how's that? Test. Okay. Okay. Now, this mic is on, but there. Now it should be going through. There. How's that? How's that? Is there too much background on? Shutting my windows. Turn off the fan. Oops. Okay, how does this work? Okay, how does this work? So, testing audio. So. Okay, good. Okay. Oh. Eric Myers left Meta.
Eric Myers left Meta.
Ah,
Ah,
I don't get to see
I don't get to see
the article.
the article.
This is Fortune magazine. Maybe I should get it.
This is Fortune magazine. Maybe I should get it.
Dude. Really? I don't want to do that right now.
I don't want to do that right
No. But
now. But
So I'm trying to clone the Bitcoin node so that the source code is available. I have another bonsai instance where the source code's already available, but I need it to be available to the AI that I'm using right now, which in Cursor, which is GPT-4, GPT-4, or it could be switched, it could be toggled. Yeah. Anyway. Okay. All right. Check out Studio. What? Which one is it then?
The only way I'm going to learn how to do this is by doing it. Um, It's loading.
What? It's not gonna work. Oh. Wrong machine. Crap.
So when we spin up our node, we don't have to sync the whole thing. Hey, I just had a crash. It crashed OBS in on my MacBook. So I'm just gonna have to fix that. What are you talking about? Let's go, Bitcoin. Sink, 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 sink. It's going up, but slowly.
Mm. Um. Oh, I forgot to stream it back out. Sorry.
Sure.
Hello? Hello? Okay. Try to find it. I don't see it. Huh? No. I don't know where the photo is. I haven't seen it. Try to find it. I don't see it. No, that's fucking awful. Okay, well, no, okay, well, last time talking about streaming in the middle of something. I'm in the middle of stuff right now. I told you. Hello? I'm in the middle of it. I've already checked. I'm in the middle of streaming. I'm dealing with Docker issues right now, so just give me a minute. Come on, why? Docker, yes. Ah, no. God. Come on. Oh, something's wrong. All